Hi guys, in this video we'll be starting a new topic, that is BJT amplifier. So up to now what we have done is we have seen the DC circuits involving BJT and we have seen some DC applications like voltage regulator and current mirror circuit. But now we'll be going on to the main application of BJT, that is we have to use BJT as an amplifier. So first let us understand what is meant by an amplifier. So an amplifier, if we talk about amplifier, it is a circuit that increases amplitude of an AC signal. Now suppose the input signal is A sine omega t. Then the output signal should be B sine omega t plus phi. There is some phase shift and the amplitude has changed. So how you can find power of xt? The power is equal to x RMS square. Now RMS of sinusoidal signal is A by root 2. So square would be A square by 2. What about power of yt? It will be simply B square by 2. Always remember, the power of an AC signal is given by square of its RMS value. Now if you see that, if we say that B is greater than A, in that case power of signal Y is greater than power of signal X. That means amplifier also increases power of AC signal. But we know that overall power of a system is conserved. Then how can we increase the power of AC signal? For that we give DC supply. I told you the DC supply in any circuit is called as biasing, which we have studied so far, and the AC supply is called as input signal. So if you want to increase the power of the input signal, you have to draw power from the DC supply. So what happens in an amplifier? It consumes power from DC biasing and supplies some fraction of power, some fraction of P to input AC signal. It does not completely send the power drawn from DC into AC, but only some fraction of the power drawn from the DC supply. That means rest of the power drawn from DC supply will be wasted or efficiency will not be 100%. Okay. Suppose it is drawing 1 watt power from the DC supply, it will send 0.5 watt to the AC signal and rest of the 0.5 watt will be dissipated in the circuit. Now see this circuit that I have shown here, the system. There is a gain. Gain is nothing but output by input. That is called as gain of amplifier, and it is the most important parameter when we talk about amplifier. Now see this input signal. I told you we take a small signal input. Why small signal? So that we can linearize the characteristic, and once it is linearized we can use superposition principle, that is we can solve separately for DC and AC. Now see the output. Output is negative of the input. See, when input is positive, output is negative. It means 180 degree phase shift. As I earlier told you, common emitter configuration gives 180 degree phase shift, and that is what I have shown here, 180 degree phase shift between input and the output. Okay. The amplitude of the output has increased, as well as there is 180 degree phase shift between input and the output. Now, ideally, how do we model an amplifier? We show an input resistance inside the amplifier. Then there is gain A, and an output resistance. So if you want to show it in more proper manner, how we show it? This is your input resistance Rin. The voltage across it is called as Vin. Then we show a dependent voltage source with gain A into Vin in series with the output resistance Rout. Now generally we connect a supply here. The source can have a certain resistance Rs and the source can have a value Vs. Similarly, we will connect load here RL. Okay, that sort of a circuit we show in case of an amplifier, and only this part of the circuit represents amplifier. Okay, the left part is source and the rightmost part is load. Okay, so amplifier is represented by a dependent voltage source whose voltage is multiple of the input voltage. It is multiplied by a factor called as the gain of an amplifier. There are certain parameters which we define for an ideal amplifier. Now what are those parameters? That this gain is equal to A. The output resistance for an ideal amplifier is 0 and input resistance is infinite. Now how I am saying these parameters for an ideal amplifier? Now see, the voltage across the load is not A into Vin because there is some voltage drop across Rout. That means the total voltage does not appear across the load due to this output resistance. But if this output resistance is 0, then the entire voltage can be obtained across the load, and that is why I am saying for an ideal amplifier the output resistance must be 0. Similarly, if you see, Vin is not equal to Vs. Why? Because there is some voltage drop across the load. Otherwise, what you can see here is Vin is Vs into Rn by Rn plus Rs, or you can say Vs by 1 plus Rs by Rn. Now if this Rn is infinite, this voltage will be equal to Vs. That means the total supply voltage will appear across Rn, and that is desirable. So Rn must be infinite. So for an ideal amplifier, the input resistance must be infinite and the output resistance must be 0. But practically this does not take place. So we want input resistance to be as high as possible and the output resistance to be as low as possible. So these are the requirements that we want to satisfy when we talk about practical amplifier. So when we talk about voltage gain, it is represented by AV, it is V0 by Vin. Current gain is represented by AI, I0 by In, and power gain by AP, which is AV into AI. Okay, so three gains we can define for an amplifier: voltage gain, current gain, and the power gain. Next, let us talk about how to model BJT in case of AC supply. Now first let us talk about these capacitors that I have shown here, C1, C2 and C3. If you see this C1 is connected with the source, C2 is connected with the output, and C3 across RE. So C1 and C2 are called as coupling capacitors. Why coupling capacitors? Because for AC source and load, they are connecting the output to the circuit and they are connecting the input to the circuit. Because when we talk about AC supply, what I told you is short circuit capacitor. if you short circuit capacitor, this Vs gets connected to base, and similarly V0 gets connected to collector. So if you want to connect the input and the output, then you have to make use of C1 and C2. Similarly, if you see C3, if you short circuit C3 in AC source, this RE will be short circuited. If RE is short circuited, ammeter will be connected to the ground. So C3 is called as ammeter bypass capacitor. Bypass means it will bypass the resistance RE and it will connect the ammeter terminal of BJT to ground. So these three capacitances are important when we talk about the AC analysis of a BJT amplifier, C1, C2 and C3. Okay. Now when we perform AC analysis of a BJT, then what we have to do is we have to short circuit DC supply. So see one thing, in case of DC supply, capacitor will be open. Why it is open? Because 1 by omega C tends to infinity. But in case of AC supply, we short circuit the capacitor. That means when you are performing DC analysis, you will open circuit this capacitor. So Vs will get disconnected. You will open circuit this capacitor. V0 will get disconnected. And you will open circuit this capacitor so that Re comes into the circuit. I also told you what is the purpose of Re. It is used to stabilize the Q point. So ammeter resistance is important for stabilization. So when we draw AC model, then we have to short circuit all DC supply. Either you short circuit the DC supply or you ground the DC supply. So when we talk about AC equivalent, then what we do is, see this. What I will do here, this is Rs, Vs, and this capacitor is shorted. These are two resistances, R1 and R2. Now this DC supply VCC will be grounded. This is RC. This is RE. And this capacitor is short circuited. C2 is also short circuited. This is V0. Okay. Now see one thing. See one thing, that this resistance Re is short circuited. That means this Re will not affect the AC model. Now see, the top terminal is grounded and the bottom terminal is grounded. So these resistances R1 and R2 are connected in parallel. So let me modify the circuit in the next diagram. So what I am saying is, this is Rs, this is Vs. Okay. Now this is this terminal base. I told R1 and R2 will be coming in parallel. So I am showing like this, R1 parallel R2. Now this is your BJT. Ammeter gets directly connected to ground due to this capacitor C3. Now this RC, if you ground this VCC, this RC is connected between collector and ground. So it means we will show RC between collector and ground. Collector, ammeter, base. Okay. So that will be the AC equivalent of your BJT or your BJT amplifier. Now there are certain terms that we define for this BJT. What are the important terms? First one is called as input impedance. Now what is this input impedance? It is Z in. It is the ratio of input voltage to input current. Okay. Now how to find this input impedance? Always remember, this is very important point, mark it. Always remember, when you want to find out input impedance, don't include the source resistance. So the voltage after the source resistance is V in and the current is I in. So remember this, input impedance does not include RS. Okay. So that is your input impedance. And as I told you, for voltage amplifier we want input resistance to be as high as possible. Next important parameter is output impedance. Output impedance is Z out is V out by I out, but in this case we make Vs equal to 0. We remove the source. So what does it mean is, this is V naught and this is I out. But always remember, if there is some resistance RL here, this is the load resistance, this RL must not be included if RL is shown here like this. This RL is not included in your output impedance. So output impedance does not include RL. Is my point clear to you? So when we talk about input impedance, we have to ignore the source resistance, and when we talk about output impedance, we have to ignore the load resistance. And the third most important parameter that we derive for any amplifier is the voltage gain. We write it as AV, V out by V in. Okay. So that is your voltage gain. And we also define one more parameter, that is overall voltage gain. That is AVS, V out over Vs. Okay. That is your overall voltage gain, AVS. So these are the important parameters that we define for a BJT amplifier or for any other amplifier. But what you have to remember in this section, when finding input impedance, ignore RS. When finding output impedance, ignore RL. Now what happens is, if you see this, we drawn the AC equivalent, but this BJT is a non-linear circuit, or you can say BJT is a semiconductor device. Now I want to remove this device and replace it by network elements like resistance, inductor and capacitor. I want to model this BJT in terms of basic network elements so that I can solve this circuit. As simple as that. I just want to solve this circuit. For that I need to replace BJT by network element, and that process is called as modeling of BJT. So now we will study different models that are defined for BJT, and the first model is called as Ebers-Moll model. Now Ebers-Moll model says that BJT consists of two diodes, one between emitter and base and one between base and collector. So see this is a NPN transistor. So there are two diodes from P to N and again from P to N. So this is your diode D1 and this is your diode D2. So these are two diodes. Now what is the question is, why we have shown these dependent sources? The reason is that these diodes are not independent of each other. If charge carriers are entering from emitter to base, these are the electrons, then they also reach the collector. That means the charge carriers flowing through this diode are also entering the second diode, and that is why if the current of this diode is IED, some part of this current reaches the collector, and what is that part? Alpha F into IED. Alpha F is called as forward current gain. Is my point clear to you? if charge carriers are entering from emitter to base, they don't exit from the base itself, but some of the charge carriers reach the collector region. That means not entire current does not leave the base, but some portion of current reaches the collector. And that portion of current is represented by this dependent source alpha F into IED. Since it is only some portion of the current, this alpha F will be less than 1. Okay. That means some part of the emitter current will also reach the collector. That is called as alpha F. Similarly, if charge carriers are flowing from collector to base, suppose if electrons are going like this from collector to base, some electrons will reach the emitter. That is why if this diode carries a current ICD, some part of this current reaches the emitter. So alpha R is the reverse current gain. Why we are calling it as reverse? When we were talking about working of BJT, what did I tell you? Charge carriers always flow from emitter to collector. So charge carriers first enter the base region and then they reach the collector region. But if you are operating in the reverse manner, that is charge carriers are entering the collector and then they are reaching the emitter, so it is the reverse process, and hence the current gain defined is your alpha R or the reverse current gain. Is my point very clear to you? So what I have done is, I have replaced the BJT by two diodes from P region to N region, but since charge carriers flowing from one diode will also affect the third region, so that effect is shown by use of two dependent sources having the gain alpha F and alpha R. Okay. So now if you apply KCL here, what is emitter current IE? IE, basically this IE should be like this. This IE should be like this because current is entering from base and collector, so it must leave the emitter. This must be IE. This arrow is incorrect. Now if you apply KCL, what is IE? IED minus alpha R ICD. Similarly, if you apply KCL in IC, IC is alpha F IED minus ICD. Okay. Now this IED is basically diode current. So what is this diode current equal to? It is equal to I E naught e to the power, since it is diode current, VBE by eta VT minus 1. Because the voltage across diode is base emitter voltage. What about ICD? It is IC naught e to the power. The voltage across this diode is VBC by eta VT minus 1. So these are the two diode currents based on which we can write down the total current of emitter and collector. What I can write down? IE is IEO e to the power VBE by eta VT minus 1 minus alpha R ICO e to the power VBC by eta VT minus 1. Similarly, this collector current alpha F IEO e to the power VBE by eta VT minus 1 minus ICO e to the power VBC by eta VT minus 1. Okay. So these are the emitter and the collector current based on this circuit. Now what is the beauty of this Ebers-Moll model? It is the most accurate model among all the models that we will be studying about BJT. There is no better model than Ebers-Moll. Then what is the disadvantage? The disadvantage is the non-linear nature because we are using exponential equation. Now when we talk about Ebers-Moll model, it is valid for all operating regions of BJT. This was one question that was asked in GATE as well. Eber's mole model is valid for all operating region, which are 4 region: active, saturation, cutoff and inverse active. So let me show you how we define for active region. For active region, what do we say? Ammeter base junction is forward biased and collector base junction is reverse biased. So what we can do is, this ammeter base is a diode. This is ammeter, this is base. And this collector base diode will be open circuited because collector base junction is reverse bias. So what is this ICD? ICD is 0. See this. This diode is reverse bias, so its current would be 0. If ICD is 0, the current source dependent on that will also be 0. So the current source above it will be open circuited like this. What about the current source here? This current is IED. So this current source will exist like this, alpha F IED. So what about this collector current? One minute. Actually, this diode was reverse. This diode was like this. We were talking about NPN. Okay, this diode was opposite. So this is your current IED and this is alpha F IED. So what about collector current by KCL? Alpha F IED. What about ammeter current? IED. What about base current? Base current is ammeter current minus collector current. So IED 1 minus alpha F. Okay. So that way we can represent any operating mode of a BJT. Like in saturation, you will forward bias both the diodes. So no element will be removed. Both the current sources will be there and both diodes will be there. In cutoff, what do? We reverse bias both the diodes. If both junctions are reverse bias, both diodes will be open. Hence, both current sources will also be open. So this is the only model of BJT which is applicable in all the operating regions, that is the 4 region. Okay. So what is the advantage of Eber's mole model? The first advantage is all operating regions are covered. Second, it can be used at any bias and temperature. What about drawback? What about drawback of this model? First of all, it is non-linear model because we are using exponential equation, or you can say large signal model. Large signal means if the AC signal is large, we cannot linearize the BJT. So non-linearity we have to use in large signal, and it uses diodes. So these are the disadvantages of the Eber's mole model. So let me summarize what we have learned so far. When we talk about AC analysis of BJT, what steps you have to take? Ground, DC supply, short circuit, capacitors, replace BJT by its equivalent model. Then we talked about one model of BJT, which is your Eber's mole model. In this we saw it is valid for 4 operating regions, all the operating regions. But this model is non-linear and it is large signal model. So generally when we talk about amplifier, we will not make use of Ebers-Moll model, but based on small signal assumption, we will try to linearize the model, and once we linearize, our circuit will be simplified, and once the circuit is simple, the gain and other parameters of amplifier could be easily calculated. So that is our objective when we talk about the other three models of BJT, the RE or the T model, the hybrid model, and the hybrid pi model. In every model, what we'll try to do? We'll linearize the circuit so that we can easily solve it as a network. So one thing that you guys have to understand, every time you might be thinking that BJT amplifier is the most difficult topic, but if you watch the future lectures carefully, whatever I am going to teach you, you will feel that BJT amplifier is not that difficult, it is overhyped, and we learn how we can use basic network analysis to solve all the amplifier problems. No problem is difficult, but as long as your basics of network analysis is clear. So I'll solve the rest of this chapter just by network analysis, and if you have good command over it, you will feel that you were wrong about AC analysis or small signal model. It is very simple thing. Okay, so we'll start other models from the next video. Hi guys, in the previous video we started with the concept of BJT amplifier. So in amplifier what I told you is we perform small signal analysis, that is we superimpose a small AC signal on a DC signal and we model BJT using the linear element. For linearization we need to have a small signal so that fluctuation in the input signal is very small. So for AC analysis, I told you for AC analysis, what we need to do is, we need to ground VCC and we need to short circuit all capacitors. Once this is done, then BJT is replaced by its equivalent model. And then we solve the circuit for mainly three parameters. The three parameters that I described were input impedance, output impedance, and voltage gain. Other than that, what I told you, is I introduced to you one model of BJT, which is Ebers-Moll model. In NPN transistor, I told you BJT is modeled as two diodes. This is your IED. This is ICD. This is alpha F IED, alpha R ICD. Okay, this is IE, IB, and IC. I told you the advantage of this model is it is valid for all operating regions of BJT, but the main disadvantage is it is large signal model and it is non-linear, so it is not generally used. From now on, whatever models we'll talk about, we'll only talk about active mode of operation, because we want to implement BJT as an amplifier. So what I told in active mode of operation, ammeter base junction is forward bias. So we show this diode, and collector base junction is reverse bias. So diode is open circuited and ICD is 0. So there is only one current source like this, alpha F IED. This is IED. This is IC, this is IB. Okay, so this I told to you in the previous video, that is in active mode of operation, ammeter base junction is forward, So we replace it with the diode. Collector base junction is reversed, so the diode is open. So in this lecture, we'll start with T model of a transistor. But remember, from now on, whatever models we'll study, we'll talk about active mode of operation. Just now what I have told you is, in active mode of operation, between ammeter and base, this is base, this is ammeter, P, N. Between ammeter and base, there is a diode. And between collector and base, there is a current source, which is suppose IED. So this current is alpha F IED. This is IC, this is IB, and this is IE. Okay. This is common ammeter, so I have shown ammeter terminal as common. This is what I have showed you here. Instead of just horizontal diagram, I have drawn it vertically, nothing more than that. Now see one thing, this alpha F is basically equal to alpha, and we can say IC is alpha IE. So what I'll do is, I will show this diode and this current will be alpha I. I am using lowercase letter for AC model. This is IB. IB and IC will make IE. Now IC can also be written as beta IB. It is equal to alpha IE as well as beta IB. And remember when we studied about diode, when we studied about AC model of diode, diode is replaced by diode resistance RD. RD was VT over ID. But here the diode current is ammeter current. So here this diode is replaced by RE, where RE is VT by IE. This IE is DC current. This RE resistance I introduced to you in the initial lectures when I was talking about common ammeter configuration. So I told you that ammeter base junction can be modeled as a resistance which is called as the input resistance RE. So how this model will look like? This diode is replaced by a resistance RE. This is the current. I can write it as beta IB or alpha IE. This is collector, base current is IB, and this current is IE. So that is the model of your common ammeter configuration. Okay, is it fine? So here, since the diode carries a current IE, the diode resistance is VT by IE. But remember, when we want to find out the resistance for AC model, we make use of DC current. If you are not able to remember this, go back to the diode lecture and see where I have introduced the AC model of a diode. Now we want to make this circuit disjoint. So what is the current in RE? Or the voltage across base ammeter VBE is IE RE. IE is 1 plus beta IB RE, or what you can say IB into 1 plus beta RE. So if we want to modify this model, this is the base terminal. It carries the base current. So between base and ammeter, you can show this resistance like 1 plus beta RE. Now if you see, the voltage between base and ammeter is IB multiplied by 1 plus beta RE. Initially also this was the voltage 1 plus beta IB RE, but I have taken 1 plus beta with resistance, so the current will now be IB. So I have shown the resistance in such a way that the current in the resistance is IB, but to keep the same voltage drop, the resistance must be multiplied by a factor of 1 plus beta. The collector current source is beta IB, like this, and this is your ammeter. So what is the current here? The current here is IB plus beta IB, or 1 plus beta IB. Okay, that is the current in this branch. But now what happens is, when we talked about common ammeter configuration, when I told to you about common ammeter configuration, I also talked about an effect called as early effect. In early effect, I told you that output characteristic is not flat but has a slope, and this is represented by output resistance R out, or you can call it as R naught, which is VA over ICQ. ICQ means Q point collector current. So that is why if you want to show the complete model, what you have to modify is, you also have to show, what you have to show is the output resistance R naught. So this is your beta IB, and here we will show the output resistance R naught. This is your collector, ammeter, and ammeter is grounded. Always remember, this R naught is very high, so in most of the problem we ignore this R naught, or we consider it as open circuit because it is in the range of mega ohm. Now if you see, if I want this VCE, this current beta IB will flow in closed loop like this. If it is going from down to up, plus minus will be like this. So this VCE is minus beta IB R naught. So it is less than 0. It means this configuration is offering 180 degree phase shift. So this I initially wrote directly that common ammeter configuration gives 180 degree phase shift, but even if you see practically, there will be a 180 degree phase shift in the common ammeter configuration. Let us see another configuration in T model, which is your common base configuration. Okay, so let me first draw common base transistor. In common base, the base terminal is common. Input is applied between ammeter and base, and output is taken between collector and base. Okay. Now, as we have seen, the ammeter base junction is replaced by a diode. This diode current is IE. Then in collector terminal, we show a current which is alpha IE, which means the current in this branch IB is IE 1 minus alpha. This is ammeter base collector. Okay. So is it fine? This ammeter base junction is replaced by a diode, and the collector base junction we have shown a current source. Now what you can do is, you can replace this diode by a resistance. What resistance we showed is RE. Okay. Then this current is alpha IE. This current is IE. So this is the base terminal. The current here is IE 1 minus alpha. And if you want to show the output resistance also, you can show output resistance like this, R0. Now this output resistance is due to, it is due to the early effect in which the output characteristics are not flat, they have a certain slope. Okay. So that is how you can represent the common base connection. Now in common collector, the last configuration is common collector. In common collector, we make use of same model as common ammeter. Okay. And remember, when we talk about NPN and PNP, when you talk about NPN and PNP, AC model is same. Now, why AC model is same? Because when we talk about AC signal is positive for one half cycle and negative for the other half cycle. That means even if PNP transistor is applied, there will be no change in the AC model. But when we talk about DC current always flows in a unidirection or in one direction. So we have to replace the current direction, or we have to interchange the current direction in PNP and NPN transistor. Like in NPN transistor, ammeter current leaves the transistor, whereas in PNP, ammeter current enters the transistor. But in AC, current reverses after every half cycle. So entering or leaving current will not affect your answer. The answer will always remain same. That is why the AC model for both NPN and PNP transistors will remain same. And the model for common emitter and common collector configuration is also same. What you have to do, even if you forget this model, replace base emitter junction by a diode and replace collector base junction by a current source, and then you can solve the circuit. So let us see how to apply this concept. So here I have shown you a common emitter amplifier. Emitter terminal is common with voltage divider biasing. Now when you perform DC analysis, the step 1 for amplifier analysis is perform DC analysis. This I have showed you how to perform DC analysis in biasing problems. Okay, for this you must have gone through the biasing problems. After performing DC analysis, we get two things, the Q point IC and VCE. Now step 2, form AC model. Now how do I form AC model? I ground this VCC and I short circuit these capacitors. If we short circuit this CE, RE becomes short circuited. So how you will draw the model? This RE is shorted, C1 is shorted, this voltage is V in. Now see, the top terminal is ground and the bottom terminal is ground, due to which R1 and R2 are in parallel. So I'll show R1 parallel R2. Since ammeter is also grounded, so I have shown this connection here. Now this collector resistance, it is connected between the collector terminal and ground, because now the top terminal is ground. So I will connect RC between collector and ground. RC and collector terminal is connected to V0. So this is your AC model. Now what we have to do is we have to replace this BJT by its T model. How to replace BJT by its T model? So what you will do is, this is V in. This resistance is R1 parallel R2. Now see the circuit of BJT. In BJT I told you this resistance is 1 plus beta RE and the current in this resistance is IB. This terminal is ammeter, this is base, this is ammeter. Ammeter is grounded. Then we connect a current source beta IB. We get this terminal is collector. So I have replaced BJT by a resistance and a current source. Then as I have shown in the model, there is this resistance R0 and RC is connected between collector and ground. This is your RC. This is V0. So what I have done is, I have replaced this much circuit. I have replaced this much circuit in place of BJT. Okay, this is the circuit of BJT. Rest of the components are same. But remember, just the when you are making the connection, you just have to remember the terminal. This is collector, base, ammeter. In base terminal, between base and ammeter, I am showing a current source. Sorry, a resistance. Between collector and ammeter, I am showing a current source. That is beta IB. Okay. Now, whenever you have to derive any parameter, let me derive one by one. First, let us go after output impedance. Output impedance is the impedance seen from this terminal, but in output impedance, we ignore RL. Since there is no resistance RL here, we don't have to ignore anything. So what is the equivalent resistance here? It can be directly seen. It is R0 parallel RC. Because this R0 is also connected to ground. So you can show like this. So these two resistances are in parallel. So output impedance is R0 parallel RC. But most of the times what happens is R0 is very high. I told in mega ohm, but RC is in kilo ohm, so their parallel combination is almost equal to RC. Then we talk about input impedance. Input impedance, I told you, ignore RS. We haven't shown any RS. So if you see from the input side, this is Zn. This resistance is also grounded due to this terminal. So these two resistances are in parallel. Input impedance is R1 parallel R2 parallel 1 plus beta Re. Sometimes if beta is high, 1 plus beta is replaced by beta. So it becomes beta Re. Okay. Now when we have to talk about voltage gain. So see this. I will replace this entire resistance by a single resistance. What single resistance I will replace it? I will replace it by a single resistance, that is Z out. So what about V0? This current will go like this, plus minus, but V0 is like this. So V0 is negative beta IB into Z out. Now we want to find the relation between V0 and Vin. When we talk about voltage gain, we want to find the ratio of V0 and Vin. If you want to find the ratio of V0 and Vin, you have to find this IB. This IB is the current in the resistance 1 plus beta Re. So how you can write IB? Since these two resistances are in parallel, the voltage across each resistance is Vin. So IB is Vin over 1 plus beta Re, or you can say Vin over beta Re, which means V0 is, if you replace IB by its value, minus beta Vin by beta Re into Z out. So this gets cancelled. So the voltage gain V0 by Vin is minus Z out over Re, which means that the voltage gain is minus R0 parallel RC by Re. As I told, R0 parallel RC is approximately RC. So minus RC by Re. The negative sign indicates that there will be 180 degree phase shift between the input and output. So remember, the output signal will be inverted version of input and it will be amplified by a factor of RC by Re. Okay. So that is how, if you replace BJT by its equivalent circuit, you can find any parameter that you want to find. Moving on, now suppose if I remove the capacitor that was here, C3. I have removed this capacitor. When you remove this capacitor and you draw the AC model, then this capacitor will be short, this will be short, this VCC will be ground. Then how you will deal with it? As I have told previously, R1 and R2 will be in parallel. So Vin will be connected at the base terminal. At the ammeter terminal, we will have a resistance Re. Okay, now this Re will not be grounded because C3 is not present. At the base, we have a parallel combination of two resistances R1 and R2. And this collector resistance, it is connected between collector and ground. So between collector and ground, we will place a collector resistance RC. And this collector terminal is connected to the output voltage V0. Now what we do in the next step? In the next step, we replace BJT by its equivalent circuit. So let me draw the equivalent circuit. So how you will draw it? One minute. I'll not show this ground. Sorry, not show this terminal. I'll connect this to ground. R1 parallel R2. This is Vin. Now we have reached the base terminal. Between base and ammeter, we will show a resistance which is approximately beta Re. Now I am saying beta is much greater than 1. So 1 plus beta is approximately beta. The ammeter terminal is connected to Re and Re is connected to ground. Between collector and ammeter, we show our current source beta IB. Then we show a resistance R0. And then between collector and ground, we show a resistance RC. That is V0. Okay. Now see this thing. Ammeter terminal is not directly grounded. Ammeter terminal is grounded by means of Re. The current here is IB. So now here what assumptions I have taken? I have taken an assumption beta is high. So 1 plus beta is approximately beta. We make another assumption that R0 is high in order to simplify the circuit. So we will treat it as open circuit. So what I'll do is I'll treat it as open circuit. Now if you want to find out the output impedance from here, Z out. In this circuit you can write down Z out is simply one resistance RC. That is your output impedance. Now when we talk about input impedance, the input impedance is Vin over In. In is I1 plus IB. So I will say Z input is V input by I input, where we can write I input is I1 plus IB. I1 is Vin over R1 parallel R2. And what about IB? IB we have to calculate. How will I calculate IB? If you see, the current here is 1 plus beta IB. So if you apply KVL in this loop, what I'll say, the total voltage is Vin. Vin is, if you see, IB into beta Re. So IB into beta Re, or actual resistance is 1 plus beta Re, plus the current in this resistance is 1 plus beta IB. So 1 plus beta IB into Re. So it is IB 1 plus beta Re plus Re, and if beta is very large, beta IB Re plus Re. Okay, that is the input voltage. So how you can calculate IB? IB you can write as Vin over beta Re plus Re. Once I know In I can calculate Z in V in upon I in, that is 1 over 1 by R1 parallel R2 plus 1 by beta Re plus capital Re. So this is actually R1 parallel R2 parallel beta Re plus capital Re. Now this capital Re is actually much greater than small re. So sometimes we also write it like this. If capital Re is much greater, beta capital Re. But this is only valid when capital Re is much greater. Now the last step is calculating the voltage gain. So I am removing these things. If you want to calculate voltage gain, see, this beta IB current comes like this. So it is coming like this, beta IB. So the voltage is plus minus like this, but V0 is opposite polarity. So what you can say, V0 is minus beta IB into RC. Now we know IB can be written as V in from this equation by beta Re plus capital Re, which means beta gets cancelled, minus RC over Re plus capital Re into V in, which means V0 by V in, which is the voltage gain, is minus RC over small re plus capital Re. Now see in the previous case. In the previous case, what was the gain? The gain was minus RC by small re. In this case, what is the voltage gain? Minus RC by small re plus capital Re. That means due to this capital Re, the voltage gain is reducing, and that I told you initially also that if you don't bypass this resistance Re, it acts as negative feedback and it reduces the gain of the amplifier. And that is the same thing that is happening here. Due to this capital Re, the gain has reduced. Okay. So what is the significance of capital Re? It stabilizes the Q point. What is the disadvantage? It reduces the gain. And that is why we use a bypass capacitor, so that capital Re does not appear in the AC analysis. Okay. Moving to another circuit. But also remember one thing, when I am teaching you all those things, you don't have to memorize these formula. Just observe how I am tackling this concept. Okay. Now the next circuit is ammeter follower. Ammeter follower is basically also called as common collector configuration. And why it is called as ammeter follower? Because output voltage is taken from ammeter. So you can say the output voltage follows the ammeter voltage, and hence we are calling it as ammeter follower. Now see how we can design the circuit. We'll first short circuit the VCC. We'll short circuit the capacitors. How will the circuit look like? See, this V in is connected to the base of transistor. So this terminal is base. This RB is connected between base and ground. So I'll show RB here. Okay. This RC is connected between collector and ground. So I'll show RC like this. This RE is connected between ammeter and ground. This is RE. Now we have to show the model of BJT between base, collector and ammeter. So what I'll do, between base and ammeter I'll show a resistance beta Re, assuming beta is much greater than 1. Between collector and ammeter I will show a resistance, a current source, which is beta IB. This current is IB. And again I am assuming R0 is open circuit. This assumption I am taking in order to simplify the analysis. Okay. So that way you can skip one step. When I was showing BJT, what I have now done is I have directly replaced BJT by its equivalent circuit. Now again I have to find the parameters of this circuit. So the first parameter is the input impedance. So input impedance is V in by I in. Now in this circuit, if you want to calculate I in, it is simply I1 plus IB. Now this I1 is V in over RB. But how to calculate this IB? See the current in this resistance. It is 1 plus beta IB. IB is coming here, beta IB is coming here by KCL, 1 plus beta IB. So if you want to find out IB, you will apply KVL like this. So you will say that V in is equal to IB into the actual resistance is 1 plus beta RE. We approximate it as beta RE plus 1 plus beta IB into capital RE. So this is 1 plus beta IB small RE plus capital RE. Now if 1 plus beta is equal to beta or beta is very high, so that way you can write down IB is V in over beta RE plus capital RE. In this case now, say this is I in. In this case now, if you calculate Z in, which is V in over I in, it will be 1 over 1 by RB plus 1 by beta small RE plus capital RE. Or what you can say it is RB parallel beta RE plus capital RE. Okay. So that is your input impedance Zin. Now if you want to find out output impedance, okay, if you want to find out output impedance Z out, how do we calculate Z out? It is V out over I out when the input voltage is 0. So in this case what you have to do is you have to ground this. If you ground this, this RB becomes grounded and we have to calculate V0 by I0. Now how will you calculate this terminal or this term V0 by I0? So now one thing, that this current will not be simply 1 plus beta IB, it will be 1 plus beta IB plus I0. So in this circuit what you can say? V0 is 1 plus beta IB plus I0 into RE. Okay. Now we want V0 by I0. So I want to remove this IB. For that what I'll do is I'll apply a KVL like this. Okay. So if I apply a KVL like this, I'll say 0. This is 0 voltage. The voltage here is IB into beta RE minus IB into beta RE, or exactly 1 plus beta RE. Then this is equal to the voltage V0. So IB is minus V0 over 1 plus beta RE. So that way what I can say is 1 plus beta IB is equal to minus V0 by RE plus I0 RE. Now when you take V0 terms on one side, so what is V0 by I0? RE over 1 plus capital RE by small RE. which is equal to Re over Re plus small re, or you can say Re parallel small re. So that will be your output impedance Z out. Okay. So in this case, don't directly say that Z out will be Re. You have to calculate V0 by I0. Otherwise, I'll show you one shortcut. Okay. When we started with T model, what I said is, if you show the resistance Re in the emitter terminal, if you show the resistance Re in the emitter terminal, I was showing it as small re. Let me show you. If you want to understand this, see. Initially, when IE current was flowing, I was showing the resistance as Re. When I transferred it to base, when IB current was flowing, I made this resistance 1 plus beta Re. So what you can say is, when you transfer the resistance from emitter to base, when you transfer the resistance from emitter to base, multiply by 1 plus beta. Similarly, when you transfer the resistance from base to emitter, you have to do opposite, divide by 1 plus beta. So see this thing. Now I'll show you how to calculate directly. See in this circuit, I want to refer this resistance at the emitter terminal. If I want to refer it from emitter to base, I'll divide it by 1 plus beta. And since beta is high, I can say I will divide it by beta. If you divide it by beta, what it will become? Re. So if it becomes small re, then what I will do is, if I refer it to the emitter circuit and it becomes small re, then what you will do is, you will show like this. Now the total input impedance is capital Re parallel small re. So remember, when you wish to refer a resistance from emitter to base, multiply by 1 plus beta or simply beta. And when you want to refer it from base to emitter, then divide it by beta. Now let us find out the output voltage upon input voltage, that is the gain of the amplifier. So now I am removing this I0. Okay, this short circuiting also I am removing. So this resistance is beta Re. This is your V0. So now the current in the ammeter resistance is simply 1 plus beta IB. Or let me solve it there itself. So I'll remove this. Okay. Now if you want to find out the voltage gain, so V0 is 1 plus beta IB into Re. But I want to find out IB in terms of Vin. So again I'll apply KVL like this. So I'll say Vin is IB into actually 1 plus beta Re, or beta Re you can say, plus V0. So that means IB is Vin minus V0 by 1 plus beta Re. If you substitute this value here, so 1 plus beta into IB will become Vin minus V0 by small re into capital Re. That means Re V0 equal to capital Re Vin minus capital Re V0. From here, if you calculate V0 by Vin, it will come out to be capital Re over small re plus capital Re. So this is positive, means 0 degree phase shift. So that is what I told you, in common collector configuration there is 0 degree phase shift and this gain is less than 1. So common collector configuration gives a low value of voltage gain. The gain is less than 1 and it provides 0 degree phase shift. Lastly, let us see what happens if we consider the source and the load resistance. Up to now I haven't considered RS or RL. So in this I am considering voltage divider bias with C3, that is the ammeter bypass. So I am showing the circuit simply. This is your supply. We will show the source resistance as well, RS. In voltage divider bias, we have a resistance R1 parallel R2. Then we have a resistance beta RE. It carries a current IB. Since ammeter has a short circuit capacitor, so ammeter is grounded. Then we have a current source beta IB. Then we have a output resistance R0, which is actually very high. Then we have a resistance RC connected between collector and ground. And now we also have one more resistance RL. This is your V0. Okay. Now the input and the output impedances are not affected, because while computing input impedance we ignore RS, and while computing output impedance we ignore RL. So what is the effect of the source and load resistance? They affect your voltage gain. Now see this, all these three resistances in parallel can be replaced by a single resistance. If you replace it by a single resistance, what you will write? We will write R0 parallel RC parallel RL. Now this current will go like this. So plus minus will be opposite to the polarity of V0. So I will say V0 is minus beta IB R0 parallel RC parallel RL. That will be the value of V0. And if R0 is very high, so you can ignore R0 and you can write down like this, RC parallel RL. Now we want to find out this IB. This voltage is called as Vin. So Vin is basically IB into beta RE, or you can say IB is Vin over beta RE, which means that you can write down V0 is minus beta by beta RE Vin into RC parallel RL, or you can say V0 by Vin is minus RC parallel RL over RE. This is called as AVL. L represents that we have assumed the load resistance RL. We have not ignored the load resistance RL. Earlier we derived, in the first case we derived the voltage gain as minus RC by RE. But now in the numerator we have RC parallel RL. So what you can say? AVL is less than AV. AV is the open circuit voltage gain where there was no load resistance RL. This gain that we derived earlier was AV. But this is V0 by Vin. This is not V0 by Vs. If you want to find out V0 by Vs, how you will do it? We have to find out Vin in terms of Vs. So if you see, these two resistances are in parallel. So what you can say, R equivalent is R1 parallel R2 parallel beta RE. Once you have this R equivalent, you can find out Vin by voltage division between RS and the parallel combination of the two resistances. So that is Vs into R equivalent by R equivalent plus RS. So that means if you have V0 by Vs, if you want to find out V0 by Vs, you will write V0 by Vin into Vin by Vs. V0 by Vin is how much? That we are writing as AVL. Okay. So V0 by Vs is called as AVS, that is considering the source resistance. So V0 by Vin, as we have shown here, it is AVL into Vin by Vs. It is R equivalent by R equivalent plus RS. Now this factor inside the bracket is less than 1. So this value is less than AVL. So what you can say? AV is greater than AVL is greater than AVS. Which means if you consider load resistance, the gain reduces, and if you consider source resistance, the gain further reduces. So due to load and the source resistance, due to the voltage drop across them, the gain of the amplifier always reduces. So if any question, it is just asking you the voltage gain, you find out V0 by Vs. Don't get into this terminology AV, AVL and AVS. Find out the final gain, which is V0 by Vs. Always in problem, the voltage gain should be overall voltage gain considering RS and RL. So let us summarize what we have learnt here. We first studied about T model of BJT. In T model, I showed you that we show a resistance beta Re like this, and then we show a current source beta IB, and this is the output resistance R0, collector, ammeter and base. Okay, this current is IB. Then we saw voltage divider bias. In that we derived the voltage gain was minus RC by RE. This small re is nothing but thermal voltage by ammeter current. Then we saw in case of unbypassed RE, in which we did not bypass capital RE, the gain was reduced. It became small re plus capital RE. And then we saw ammeter follower configuration. In ammeter follower, we saw that the voltage gain became minus Re by Re plus capital Re, which is less than 1. Sorry, it was plus, which means 0 degree phase shift. The other two voltage gain were negative, which means 180 degree phase shift. And I told you, due to RS and RL, the voltage gain reduces. Hence, AV is greater than AVL is greater than AVS. So voltage gain keeps on reducing if we consider the load and the source resistance. Okay. So in this entire topic, you just have to understand how to draw the BJT model. So in next video, I'll tell you how to solve problem by constructing network and without memorizing any direct formula. That we'll see in the next video. Thank you. Hi guys, in the previous few videos I have showed you how to design the T model of the transistor, which is also called as the RE model. So in this video I'll solve some problems completely for you, in which we'll derive all the amplifier parameters such as voltage gain, input impedance and the output impedance. Okay, so I'll show you how to perform the complete analysis. So let us see the first problem. It says for the common emitter fixed bias configuration, we need to find dynamic resistance, input resistance, output resistance and voltage gain. Now the first thing that it is asking is dynamic resistance Re. We know Re is nothing but Vt by IE, where IE is the DC current. So for that we need to perform DC analysis first. Always remember, whenever you face a problem based on amplifier, first we perform DC analysis and then only we go for AC analysis. Okay. So for DC analysis, when we are talking about DC analysis, what did I tell you about capacitor? The capacitor will be open circuited. If capacitor is open, this voltage drop is 0.7. Okay, this current is IV. Since capacitor is open, the same current will flow through 470 k ohm. Now what we will do is, we will apply KVL like this. Okay, so we will write 12 minus 470 IB minus 0.7 equal to 0, which means IB is 11.3 by 470. So this IB will come out to be 24.04 microampere. Now since it is talking about amplifier problem, you don't have to check the region of operation. You can always assume active region. So I'll write IE is 1 plus beta IB, which means 51. 101. Beta is given as 100. 101 into 24.04. So it will come out to be 2.428 milliampere. Now once we have IE, I can find out the dynamic resistance VT by IE. Now VT you can take as 26 millivolt by 2.428 milliampere. So it will come out to be 10.71 ohm. So that will be the value of ammeter resistance RE. So first part is solved. Now to find out other parameters, we need to form the model of this transistor. Okay, so I am forming the model. So when we are talking about now AC analysis, then what will happen? Capacitor will be short circuited and VCC will be grounded. So see, what I'll do is, I'll ground this voltage. That means first of all I'll show VI. Okay, now see this 470 kilo ohm resistance. It is connected between base terminal and ground. So this is base terminal. This is 470K and this one is base. Now between base and ammeter, we connect a resistance in transistor model equal to beta RE. Since beta is high, instead of 1 plus beta RE, you can write beta RE. Then this is your ammeter terminal. Now if you see, ammeter is connected to ground. The current in this resistor would be IB. Now for collector terminal, the current between collector and ammeter will be beta IB in parallel with the output resistance RO. This is your collector terminal. Now see this 3 kilo ohm resistor. It is connected between collector and ground. So 3 kilo ohm will be connected between collector and ground. And the collector terminal is connected to V0. This capacitor is shorted, so collector terminal is directly connected to V0. Now we need input resistance. The input resistance is always taken ignoring the source resistance. Here there is no resistance in series with VI, which means there is no source resistance. This is the input resistance RI. So how you can write input resistance? 470 kilo ohm in parallel with beta RE, or you can write 100 RE. Okay, so RE was 10.71, or you can write 100 RE is 1.071 kilo ohm. Now since 470 kilo ohm is much larger than 1.07, so this is approximately 1.07 kilo ohm. Now when we talk about output resistance, we ignore the load resistance. See, there is no load resistance here. That means output resistance is parallel combination of this 3K and R0. If you see, the lower terminal of R0 is connected to ground and the lower terminal of 3 kilo ohm is also connected to ground. So this R0 and 3 kilo ohm are in parallel. So what I will write down is Z0 is R0 in parallel with 3K. R0 is given as 50K, which means 50 into 3 by 53. So it will come out to be 2.83 kilo ohm. Now the last step is the voltage gain. See now, since you have combined R0 and 3K in parallel and calling it as the overall output resistance, this is R out. So this beta IB current will be flowing like this. So this will be plus minus and the current will be beta IB. So what you can say is V0 is minus, because the polarity is opposite, current is beta IB and resistance is R out. Is it fine? Because V0 will be like this, plus minus, but the actual polarity is opposite. Now this current IB, if you see that 470 kilo ohm and beta RE are connected in parallel, so they will have same voltage across them. So what we can say is that IB is input voltage by beta RE. So VI by 1.071 kilo ohm. So V0 is minus 100 into R out is 2.83 kilo ohm into VI by 1.071. So you can say V0 by VI is minus 100 into 2.83 kilo ohm by 1.071 kilo ohm. So this will come out to be how much? It will come out to be minus 264.25. Okay, and that is a high value of gain, and that is why we say common emitter amplifier is the best form of the voltage amplifier. It offers high gain. So remember, you don't have to memorize any formula. The only formula in RE model is that RE is VT by IE. This is the only formula that you have to remember. Other than that, you always form the circuit and find the gain. Let us see another example. Next example is for the voltage divider bias circuit. We have to find 5 parameter: dynamic resistance, input resistance, output resistance, and the voltage and current gain. Now before solving for AC analysis, we need to perform DC analysis. Again, as I have told you, in DC analysis, capacitor will be open. So this capacitor and this capacitor will be disconnected. Now, what is the method that we studied in voltage divider biasing? We first find out the Thevenin voltage. How to find Thevenin voltage? By applying voltage division between these two resistances. So VTH is 22 into 8.2 by 56 plus 8.2. That will come out to be 2.81 volt. Then we find out Thevenin resistance, which is 8.2 in parallel with 56. So it will come out to be 7.152. Now what I'll do is I'll form the Thevenin equivalent. So what I'll do is I'll show a Thevenin voltage, that is 2.81 volt. Then I'll show a Thevenin resistance 7.152 kilo ohm, and then we'll draw the BJT. For DC analysis, capacitor is open, so this RE will be in the circuit. Okay, let me remove these parameters in order to draw the complete circuit. Then we will draw the collector resistance 6.8 kilo ohm, and then this is 22 volt. Now what I'll do is, this current will be IB, this current will be IE. So I'll apply a KVL here. So what I'll write, 2.81 minus 7.152 IB minus base emitter drop is 0.7 minus 1.5 into IE. IE is 1 plus beta, beta is given as 90. IB, IE is 1 plus beta IB. So from here we can find out IB, and then you can write IE is 91 IB. So if you solve this, IE will come out to be 1.41 milliampere. Okay, that will be your IE. Approximately this value will come out. Okay. Now once we have this IE, what I can write down, RE, that is the dynamic resistance, is VT by IE. Now VT you can take as 26 millivolt by 1.41 milliampere. So this resistance will come out to be 18.44 ohm. Okay, and that is the basic purpose for DC analysis of finding the dynamic resistance RE. Now the next step what I'll do is, I'll draw the AC circuit. Okay, so I'm drawing it on the next page. For AC circuit, what we do is, we ground the DC supply and we short circuit the capacitor. Now if you short circuit this 20 microfarad, this 1.5 kilo ohm resistance is shorted, and also if you see, the top terminal is grounded, the bottom terminal is also grounded. So what happens? 56 kilo ohm and 8.2 kilo ohm resistances are in parallel. So when we draw the AC circuit, first there is input voltage, then the resistance 56 kilo ohm and 8.2 kilo ohm are in parallel. Then this is your base terminal. Then this resistance here is beta RE. Then this is ammeter. Now see, due to this 20 microfarad capacitor, this ammeter is directly connected to ground, or you can say it is bypassed. So ammeter is connected to ground. Then we have a current source, a dependent current source, which is equal to beta IB. IB is the current here. This current source is connected in parallel with R0. Then see this resistor 6.8, it is connected between collector terminal and ground, because 22 volt is ground. So between collector, this is collector, between collector and ground we have a resistance 6.8 kilo ohm, and this voltage is V0. Okay. So now RE we found as 18.44 ohm, beta is R90, R0 is 50 kilo. Now we don't have to do anything with the previous circuit, we just have to solve this. This also we derived as parallel combination as 7.152 kilo. So first let us see the input impedance. Always remember, in input impedance we ignore the resistance RS, but in this circuit there is no resistance such as RS. RS is the source resistance, which you will always find connected in series with the input. Since there is no series resistance, we will assume that there is no RS. Don't consider this 7.15 kilo ohm as RS. RS is the series resistance with the source. So ZI is 7.152 kilo ohm in parallel with 90 into 18.44. So this will come out to be 1.35 kilo. But remember the units, this is in kilo ohm and this will come out in ohm. Always take care about the unit. Now what about output impedance? If we see from here, The output impedance is 6.8 kilo ohm in parallel with R0, or you can say 6.8 kilo in parallel with 50 kilo. So it will come out to be 5.98 kilo ohm. Now what we do is, we replace this parallel combination by a single resistance which is equal to Z0. Okay, like this. Now this beta IB current will flow like this. So plus minus will be opposite. So you can say that V0 is minus beta IB into Z0. How to find this current IB? This voltage is VI. So VI over beta RE, which means V0 is minus beta VI Z0 by beta RE. Or you can say the voltage gain is minus Z0 by RE, which means minus 5.98K by 18.44 ohm. So this voltage gain will come out to be minus 324.61. The last thing that I asked is the current gain. For current gain, you have to see we have given I0 in 6.8 kilo ohm. That means if you break this Z0 again into its two components, I0 is the current here. Okay. So if you see, the total current is beta IB. So what is I0? I0 can be found out. This is R0. I0 can be found out by current division, because current will divide into two parts. But see, beta IB is like this. So the actual current in the two resistances will be like this. These two currents will combinedly form beta IB, but I0 is shown downwards. Okay, 1 minute. If you see the actual direction of I0, see here, I0 is given from ground towards collector. See this I0. I0 is from ground towards collector, which means I0 is like this, from ground towards collector. So I0 can be determined using current division. So beta IB into R0 by R0 plus 6.8. That is I0. What about input current? The input current is nothing but it is VI over ZI. ZI means the total of these two resistances. Because we need total current, so I am taking total impedance. Also you can write V0 in another manner instead of current division. V0 is nothing but minus V0 by 6.8K. See, V0 is like this, plus minus. So the current should be downwards, but I0 flows from ground towards collector. See this figure. I0 is shown from ground towards collector. So ground towards collector means upwards, but based on V0 it must be downwards. So minus V0 by 6.8K. So what you can do is, you can write down current gain as output current by input current. If you divide these, you will get minus V0 by VI into ZI by 6.8K. Minus V0 by VI is 324.61. ZI is 1.35 kilo ohm and upon 6.8. So this current gain will come out to be 64.45. So that way you can calculate the current gain. So that is what I told. The current gain in common ammeter configuration is moderate, whereas the voltage gain is very high. Okay. So if you can draw this circuit, the circuit that I have drawn, you can find any parameter by simply performing network analysis. So let me show one more example. Again we have a common ammeter configuration. but it is saying neglect the effect of early voltage. We know that output resistance is VA by ICQ. Neglecting the effect of early voltage means VA is 0, which means R0 would be, VA is infinity. So R0 will be infinity or open. So whenever in any question you see that it is saying neglect the early effect, you always have to ignore the value of R0. But again, to find out dynamic resistance, we have to first perform DC analysis. So let me show you the DC analysis. Again, in DC analysis, how you will start? You will open circuit the capacitor. So this will be open, this will be open. This current is IB, this current is IE. So by KCL, this current will also be IB. Now I will apply KVL in this loop. So what I will write? 12 minus 220 IB minus 0.7 minus 3.3 IE. Now you need IE. So what I will do is 12 minus 0.7 is 11.3. Now IB is IE over 1 plus beta, means 1 plus 100. So from here I can directly calculate IE. So if you see what is the value of IE, you will come to know it is 2.062 milliampere. Based on this, I can write RE as VT over IE, 26 millivolt over 2.062 milliampere. So it will come out to be 12.60. So our first part is solved, as well as we have got the parameter by which we will draw the equivalent circuit. Now for AC analysis, we will ground this and we will short circuit the capacitor. Now see this, VI will be connected to the base terminal. Let me draw this. VI gets connected to the base terminal. Now see this 220 kilo ohm resistor. It is connected between base and ground. So this 220 kilo ohm resistor is connected between base and ground. Now we know between base and ammeter, we always connect a resistance beta Re, which carries a current IB, or we can show for AC in lower case like this, IB. Now this is our ammeter terminal. Now see the ammeter. Ammeter is connected to a resistance of 3.3 kilo ohm. So ammeter is connected to a resistance of 3.3 kilo ohm. And ammeter terminal is also connected to V0. So ammeter is also connected to V0. Now between ammeter and collector, what we do is we show a current source beta IB. Now it has told us that R0 is infinity, so there will be no resistance in parallel with beta IB. This will be open. Now see this collector terminal. This collector terminal directly gets connected to ground. So this is our collector. So we'll connect the collector terminal directly to the ground. That means this current is beta IB. This current is also beta IB. So based on this, I can say that this current is 1 plus beta IB. Now the first thing first, what we need is the input resistance Zi. To find input resistance, what we need is Vi over Ii. Now Ii is made of two currents. It is I1 plus IB. Now I1 is simple, Vi over 220 kilo ohm. What about IB? For IB, what I will do is I will apply KVL like this. So I'll say Vi is Ib into beta Re plus 1 plus beta Ib into 3.3 kilo ohm, which means I can say that Vi is Ib beta Re plus 1 plus beta, if beta is high, is approximately beta. Okay. Now beta is given as 100, so I am taking beta as high. Now what is Re that we found out? Re was 12.6 ohm. So from here I can say that Ib is Vi over 100 times 3300 plus 12.6, which means you can write down I as Vi by 220 kilo ohm plus Vi by 3312.6 into 100, which means Vi by 220 kilo ohm plus Vi by 331.26 kilo ohm, which means Zi, which is Vi over Ii, is basically 220 kilo ohm in parallel with 331.26 kilo ohm. So the both parallel combination will come out to be 132.72 kilo. That means input impedance is very high. Now we have got the input impedance. What we need next is the output resistance. Output resistance is nothing but V0 over I0. Now if you take I0 also, we will say that I0 is the current here. But for that, V input has to be grounded. So now let me delete this. We'll just remember that input resistance we determined as 132.72. So I'll write down the parameter that I have derived. I will write down that we have derived Zi as 132.72 kilo ohm. Remember, when we talk about Z0, it is V0 by I0, but when Vi is 0. So I have grounded this Vi and I have shown the current I0 here, which means the total current is 1 plus beta Ib plus I0. Now what I will do is, I'll apply KVL like this. So 0 minus Ib into beta Re minus 1 plus beta Ib plus I0 into 3.3k, which means Ib into beta Re, 1 plus beta is approximately beta, beta into 3.3k is minus I0 into 3.3k. Okay. So Ib is equal to minus I0 into 3.3k by beta 3.3k plus 12.6 ohm. Now once we have Ib, what I can do is, I can figure out the value of V0. V0 is how much? 3.3k into 1 plus beta Ib plus I0. Okay. So if beta is high, you can say 1 plus beta is beta Ib plus I0. From here we can find out beta Ib. Beta Ib is minus I0 into 3.3k by 3.3k plus 12.6, which means if I remove this, okay, which means if I take I naught common, V naught by I naught is 3.3K. 1 minus 3300 by 3300, 12.6, which means 3.3K into 12.6 by 33, 12.6. So this output impedance will come out to be 12.438 ohm. So that is the output impedance. Otherwise, what I have told you earlier is just refer this resistance into ammeter. When you want to go from base to ammeter, you divide by beta. So this you could have directly written as RE parallel 3.3K. When you go from ammeter to base, you multiply by beta. When you go from base to ammeter, you divide by beta. So you could have referred this resistance and got this answer directly. Now what remains is the ratio of V0 and Vi, or you can say the voltage gain. So now I will write down the value of Z0 also, which I have derived. So Z0 is 12.438 ohm. Now we want to know the ratio of V0 and Vi. So I have told you the direct method as well as the conventional method of finding the output resistance. I will remove this short circuiting. So how to find V0? In this case, V0 is 1 plus beta IB into 3.3K. If you apply KVL like this, you will write Vi is beta Ri into IB plus 1 plus beta IB into 3.3K, which means V0 by Vi, if you take, IB will get cancelled. 1 plus beta into 3.3K by beta Re plus 1 plus beta into 3.3K. Now if beta is high, 1 plus beta is approximately beta. Beta into 3300 ohm, beta into 12.6 plus beta into 3300. Beta will get cancelled, so it will be 3300 by 3300, 12.6, or you can say 0.996. So as you can say, the voltage gain of common collector or ammeter follower configuration is almost 1. Okay. Why ammeter follower? Because V0 is connected to ammeter terminal. See here, V0 is connected to ammeter. So it will follow the ammeter voltage and hence it is called as ammeter follower. The voltage gain is almost equal to 1. So in common ammeter configuration, we have high voltage gain, but in common collector, the voltage gain is approximately 1. So this is how you tackle any problem based on RE model. So what you have to do is you have to majorly focus on designing the circuit and then apply network analysis to find all your answers. Okay. So that will be all from this lecture. In the next lecture, we will see a new model for BJT. Thank you. Hi guys, in this video we will be starting a new model of BJT which is called as the hybrid equivalent model. Now what happens is that BJT can be treated as a two-port network. How? BJT has two ports, one for taking the input and other for delivering the output. So the port on the left hand side can be called as the input port and the port on the right hand side can be called as the output port. So it can be treated as a two-port network. That means the two-port parameters that we define for a two-port network are also valid for your BJT. Now what are the two-port parameters that we study? We study about Z parameters, Y parameters, we study about H parameters, G parameters, T parameters and T dash. So in this model what we are going to do is we are going to use the H parameters of two-port network. So how do we write H parameters? V1 is H11 I1 plus H12 V2. What about I2? I2 is H21 I1 plus H22 V2. So these are the equations based on H parameters. We also write these equations in terms of a matrix. V1 I2 is H11, H12, H21, H22 and I1, V2. Okay, that is in the matrix form. So here since V1 and I2 are on the left hand side, this V1 and I2 will be called as the dependent variable, and since V2 and I1 are on the right hand side, they will be called as independent variables. Okay. Now if you want to find out each and every one of these parameters, how you will write it down? H11 from this equation. H11 is V1 over I1, but for that V2 must be 0. V1 by I1 can be called as input impedance when output is short circuited. Since it is impedance, its unit will be ohms. Voltage by current has the unit ohms. Why input impedance? Because it is ratio of input voltage and input current. Similarly, H12 V1 by V2 when I1 is 0. V1 is the input voltage, V2 is the output voltage. So it is reverse voltage gain. Reverse voltage gain because voltage gain must be output upon input voltage, but it is input by output. And here since current is 0, so you can say that input is open circuit. Since it is voltage upon voltage, it will be unitless. Similarly, H21 I2 by I1 when V2 is 0, simply I2 by I1, but second term must be 0. So that is your current gain. But when output is short circuited, current gain is also unitless. Okay. Output is short circuit because I am taking output voltage as 0 and 0 voltage implies short circuit. Similarly, H22 is I2 by V2 when I1 is 0. So I2 by V2 is output, current by voltage is admittance when input is open circuit and unit of admittance is mho or Siemens. Okay. So these are the four parameters that we will be using when we are talking about the hybrid model of BJT. Okay, so in this model what we are doing essentially, we are treating BJT as a two-port network, and we are using the two-port network or two-port parameters to define the relation between the input and the output port variables. Now what we do is, we change that H11 is written as HI when we talk about BJT. H12 is written as HR. H21 is written as HF. And H22 is HO. The unit of HI, ohm, unit of HO, Siemens, and these two are unitless. So what you can now write is, V1 is HI into I1 plus HR into V2, and then I2 is HF I1 plus HO V2. Now since HI has the unit ohms, it is shown by a resistance, and this is a voltage. So this you can show like, actually it has to be shown like this. Practically this will be a dependent voltage source, because it is depending on the output variable V2. So HR V2. So the first equation is nothing but, it is an equation of KVL on the input side. The second equation involves current. So this is an equation of KCL. The first will be a dependent current source HF I1. The second thing is admittance. If it is admittance, the resistance will be 1 upon admittance, or you can say 1 by HO. This is V2 and this is I2. Is it fine? 1 by HO has the unit ohms. But if you are just writing HO, you have to remember that the units are mho or Siemens. That is, we just have changed the names of the two-port parameters H11, H12, H21 and H22. But these variables are the same variables or the same parameters that are defined in a two-port network. Now the special thing about this circuit is that this circuit is applicable to all configuration of BJT. All configuration means it is applicable for common emitter, common base, common collector, and it can be applied for any three-terminal device. Why any three-terminal device? Because one terminal we take as common, and hence we define two ports, one as the input port and one as the output port. That is the most special thing about this model. This model is the easiest model. Why? Because you don't have to change the circuit based on the configuration of BJT. This circuit will remain same, only the parameter values will change. That is, the value of HI for different configurations can be different, but the parameter will always remain as HI. So it is a generic model which is not dependent on the configuration of BJT in the circuit. Is it fine? So now when we see the complete model, for complete model what I have done is, I have connected a source Vs in series with Rs. Similarly, we have connected a load RL across which we have shown the voltage V0. But remember, the current I2 is like this. Now see if we replace this BJT. If we replace this BJT or two-port network by its hybrid equivalent, so you will show HI, this is HI, current I1, a dependent voltage source HR into V2, a dependent current source HF into I1, a resistance 1 by HO, this current I2, voltage V2, and then a load resistance RL in which current I0 is flowing. This is plus, minus, plus and minus. Okay. But remember, when we are talking about the input resistance, we will ignore RS. That is, input resistance will be nothing but it will be V1 over I1. You have to take the voltage after RS. That is, the voltage of RS or RS should not be included in the input resistance. Similarly, R0 will be V2 by I2 when V1 is 0. That means RL does not include, or RL is not included when we are talking about the output resistance. Okay. So now for this model, what I will do is I will try and derive different parameters for the amplifier, such as input resistance, current gain, voltage gain and output resistance. So I will try and derive these parameters. So the first parameter that I am starting on is the current gain. Okay. So current gain that I am deriving right now is AI, which is I0 over I1. Okay. Now see this figure. These two arrows are in opposite direction. So you can say I0 is minus I2. So you can also write it as minus I2 by I1. Okay. That is your current gain. Now we know I2 can be written as, from the second equation of two port parameters, HF I1 plus HO V2. But we need I2 in terms of I1. That means we have to eliminate this V2. How to eliminate this V2? V2 is simply V0, which is I0 into RL. Now this I0 into RL, since I0 is minus I2, it is minus I2 into RL. So what you can say from this equation, I2 is HF into I1 minus H0 RL into I2. So you can say I2 is HF over 1 plus H0 RL I1. So the current gain will be minus I2 by I1, or you can say minus HF by 1 plus H0 RL. Okay. So that is your current gain I0 over I1. So what I have done is I have simply solved this network to find the current gain. The next parameter that we will be deriving is the input resistance Ri. Now as I told you, in input resistance we do not consider Rs. So it is simply V1 over I1. Now we know from two port parameter V1 is Hi into I1 plus HR into V2. Now we know that V2 is nothing but the output voltage. So V0, this is I1, Hi I1 and V0, how can we write? I0 RL. Just now we saw that I0 is minus I2. Okay. Or you can say, you can also write like this. Don't replace I0 by minus I2. We have just now derived, we can do one thing, we have just now derived that I0 by I1 is the current gain AI, which means I0 is AI into I1. So you can write down V1 is Hi I1 plus HR AI RL I1. which means V1 by I1, which is equal to Ri, is Hi plus Hr Ai RL. If you substitute the value of Ai, Hi minus Hr into RL into HF by 1 plus HO RL. Okay, that will be the input resistance. Next, let us derive the voltage gain. The voltage gain that I am talking about is simply AV, not the overall voltage gain. This AV is nothing but V2 by V1, or you can say V0 by V1. Now, as you can see that V0 we have just written as I0 into RL, and V1 from here I1 into Ri. I0 by I1 is Ai, RL by Ri. So now what we can do is, once we have this data, if you want to simplify it, current gain is how much? Minus HF by 1 plus H0 RL. What about Ri? Hi minus HR RL HF by 1 plus H0 RL. Take this term as LCM. So minus HF RL by Hi 1 plus H0 RL minus HR HF RL. So that will be your voltage gain. But remember, this is not the overall voltage gain of the circuit. It is simply V0 by Vi. Now when you want to find out the overall voltage gain, overall voltage gain means V0 by Vs. You can write it like this: V0 by V1 into V1 by Vs. Now see this. In this circuit, the resistance here, the overall resistance here is Ri. So if I redraw this circuit, what I can draw is, this is Vs in series with Rs, and then I can replace the entire circuit by Ri, across which we have the voltage Vi. Now since these two are in series, you can apply potential division. So what you can say? V1, Vi is actually V1. V1 is Vs into Ri by Ri plus Rs. V0 by V1 is AV. AV into Ri by Ri plus Rs, because V1 by Vs will be Ri by Ri plus Rs. Okay. So what I have done is, I have replaced the entire circuit by simply, what I have done simply is, I have simply replaced it by an input resistance Ri, and then I have applied potential division. So if you see, this overall voltage gain AVS will be less than AV. Why less than AV? Because this factor multiplied with AV is less than 1. Now when we talk about overall current gain, in that case, what you have to do is, you have to replace this voltage source by a current source. How to replace this voltage source by a current source? By means of source transformation. So what I'll do is, I will show a source transformation Is, current source in parallel with a resistance Rs. Then the entire circuit will be replaced by input resistance Ri, and this is the current I1. So what you can say is I1 is Is by current division, Rs by Rs plus Ri. So overall current gain means I0 by Is. Again you can write it like I0 by I1 into I1 by Is. I0 by I1 is Ai. I1 by Is is Rs by Rs plus Ri. So as you can see, this factor, that is the ratio of resistances, is less than 1. So this product will be less than Ai. So you can say that due to the source resistance, overall current gain is less than the current gain without any source resistance. Okay. Now the last parameter that I have to find is the output resistance. But remember, when we are talking about output resistance, we will never consider the load resistance. So when we want to find out output resistance, we will short circuit the supply. I am redrawing the circuit. I have short circuited the supply. This resistance is Rs. This voltage is V1. This is actually Hi. This is I1. The voltage source here is a dependent voltage source, HR V2. Then we have a dependent current source, HF I1. Then a resistance which is 1 over HO. And then we will not show RL, but here I will show a source VDC, or you can say simply V, and a current I. So what you can say is the output resistance R out is V by I. So what I have done here is I have removed the independent sources, and then I am taking the Thevenin resistance or the resistance as the ratio of voltage and current. Okay, that is the general method that we see in network analysis. To find equivalent resistance, we have to remove the independent sources and we apply another independent source to take the ratio of voltage and current. Now this I is sum of two currents. I is I dash plus HF I1. Now this I dash is nothing but V over 1 upon H naught. V over 1 by H naught is H naught into V plus HF I1. Now I need the ratio of V and I, so I need to eliminate this I1. This is HR V2. V2 is the voltage here, which is equal to V. So you can also call it as HR V. Now apply KVL in this loop. If you apply KVL in this loop, you will write minus I1 RS minus I1 HI minus HR V equal to 0. So I1 is minus HR V by HI plus RS. So if you substitute in the I equation like this, H naught V minus HF HR V by HI plus RS. So which means V by I is HI plus RS, H naught HI plus RS minus HF HR. So that is your output resistance R naught. Okay, that is HI plus RS over H naught into HI plus RS minus HF HR. Okay, so that is how you find the output resistance, by connecting an external source and taking the ratio of voltage and current across that source. So these are the general parameters that we have derived for the case of your hybrid equivalent model. Now when we study about a common configuration like right now I am talking about the first configuration, which is common emitter. So in common emitter, what I do is I have 4 parameters: HI, HR, HF, H0. To show that we are talking about common emitter, what we do is we place a subscript E like this. So if you see a E in the subscript, you will understand that it is a common emitter configuration. As I have told you, the circuit will remain same. The only thing that will change is the value of these parameters based on configuration, whether it is common emitter, common collector and common base. Since it is common emitter, the input current is base current and the output current is collector current. Okay. So input current is base current, output current is collector current, emitter terminal is common. The input voltage is base emitter voltage, the output voltage is collector emitter voltage. So how you will write the equations? We know that so far we have written like this: HI I1, HR V2, HF I1 plus H0 V2. Now we will replace these by relevant parameter. The V1 for common emitter is VBE, VBE. HI is replaced by HIE. The input current is IB, IB. HR is replaced by HRE. The output voltage V2 is VCE. Then I2, I2 is IC. HF is HFE. I1 is IB. H0 is H0E. V2 is VCE. Okay. Now we know that the ratio of collector to base current. We have studied that the ratio of collector to base current is beta. So we say that HFE is actually equal to beta. Okay. So in this parameters, HFE is equal to beta, and you see that HRE and HOE are multiplied with VCE. So we say that HOE and HRE represent, what do they represent? Early effect. Now let me explain how they represent early effect. See, this is the input side equation and this is the output side equation. Now understand one point of mine. In early effect, what did I tell you? In early effect, I told you that as you increase the reverse bias across the collector base junction, the depletion layer grows. Okay, that is what I told you. By increasing the reverse bias, the depletion width will increase. Now this depletion width extends into the base region. As the depletion width extends into the base region, what happens? The base width will become small. If you increase more and more the depletion width, the region will become smaller. And I told you, as the region becomes smaller, the concentration gradient increases, and if concentration gradient increases, the diffusion current increases. So what I told you is, if you increase VCE, reverse bias increases, depletion width increases. Depletion width increases means base width becomes smaller, concentration gradient increases, diffusion current increases, due to which emitter current increases, collector current increases, but base current reduces due to this. Okay. So if you see, by increasing VCE, IC is increasing, so it represents early effect. Similarly, collector voltage is affecting the input side also, so HRE also represents the early effect. Getting my point? So remember this, HOE and HRE always represent early effect. So if someone says you that ignore early effect, then you can say that HRE and HOE can be taken as 0. So if someone says you that we have to ignore early effect, then you take HOE equal to HRE equal to 0. So based on this, what we do is we simplify the model. How do we simplify? If HRE becomes 0, you will remove the dependent voltage source, and if HOE becomes 0, the output impedance will be open circuited. This is HIE, IB, VBE, VCE and IC. Okay. So now what we did earlier is we derived the current gain as minus HF plus 1 plus H naught RL. Now since we are talking about common emitter, you will write as minus HFE over 1 plus HOE into RL. Remember one thing here, RL is nothing but the resistance connected at these terminal. If I say that this HOE into RL is less than equal to 0.1, 0.1 means 10 times less than this one. 1 plus very small value, 1 plus very small value is approximately 1. So you can say that current gain is minus HFE. Is it fine? So that you can do only if HOE into RL is less than 0.1. So this condition is very important. This you have to remember, that when can you ignore HOE? You can ignore HOE in two cases. Either the question says that you have to ignore early effect, or HOE into RL is less than 0.1. Then the next thing that we derived was input resistance. Just now we derived input resistance. It was HI plus HR AI RL. Now here if you are ignoring HR, it will become HI, and which is equal to HIE. So here we have ignored early effect, right? If we have ignored early effect, that means I am saying that HR can be taken as 0. Now what we did then is the voltage gain. The voltage gain was AI into RL over RI. AI is now coming as minus HFE, RL over HIE, and the overall voltage gain can be derived using voltage gain with voltage division. RI over RI plus RS. RI is HIE over HIE plus RS. That also we derived in the previous derivation. And here what you can say is, this is the overall voltage gain and this is simply the voltage gain, that means without source resistance RS. So what you have to remember in this is, mostly this circuit will be used in which we have ignored the early effect. But what is the condition of ignoring HOE? The condition is that HOE into RL should be less than 0.1. So let me summarize what we have covered in this video. We have seen that BJT amplifier can be treated as a two-port network in which we can write V1 is H11 I1, or I will directly write, we wrote HI I1 plus HR V2. I2 is HF I1 plus H0 into V2. Then we saw in common emitter configuration, we will modify the input voltage is base emitter voltage HIE into base current, and the output voltage is the collector to emitter voltage. Output current is collector current HFE IB plus HOE VC. In this case, this HFE is actually equal to beta, and also we say that we ignore HOE when HOE into RL is less than equal to 0.1. Also, when we say that ignore early effect, then we take HOE equal to HRE equal to 0. And we form a very simple model like this. This is HIE, IB, VBE, this is HFE, IB, and this is IC. Okay. In this case also I can write down one more relation. This HIE is nothing but beta RE. Okay. You can directly compare it using the T model, because in T model what was happening? This was beta RE and this current source was beta IB. So the same model I am forming here. If you see, just the naming has changed. Beta RE is replaced by HIE and beta IB is replaced by HFE into IB. So on comparison, you can also say that HIE is nothing but beta RE. So this model is same, just the method of deriving, the way of deriving has changed here. We have approached it using two-port network without using any physical process that is going on inside the BJT. Okay. So we'll discuss more on this hybrid equivalent model in the next lecture. Okay. So just now we have introduced to you the hybrid equivalent model and we have seen how to apply in the common emitter configuration. More about this we'll discuss in the next video. Thank you. Hi guys, in the previous video I introduced to you the concept of hybrid equivalent model and I told you we can use H parameters for BJT amplifier. Okay, this we studied in the last video. So I told you the equations are something like this: HI I1 plus HR V2. Then I2 is HF I1 plus HO V2. Then I told that HR and HO represent early effect. Okay, they represent the early effect case, and hence when we ignore the early effect, then we can make a simplified model just like this. If we ignore the early effect, this is V1, this is I1, this is HI, this is HF I1, and this is I2. So if we ignore the early effect, the simplified model of H parameters will look something like this. Then I told for common emitter amplifier, we change these equations to something like this: VBE, HIE, IB, HRE, VC. Then IC, HFE, IB plus HOE, VC. Then I said that this HFE is actually equal to beta and HI is beta RE, and the model is same as the RE model or T model. If we compare them, then it is same as the RE model or the T model of BJT. And we derived the current gain. The current gain was minus HFE. The voltage gain came out to be minus HFE RL by HIE. The input resistance came out to be HI. These parameters we derived in the previous video. So in this lecture, what I'll show is how you can use the H parameter model for finding different parameters for an amplifier. Okay, that we'll study in this lecture. So the first amplifier that I am taking is common emitter amplifier with bypassed RE. So how I will show this amplifier? This is RC. This is RE with a bypass capacitor. This is RE, this is CE. This is C2, this is V0. Okay. Then what I can do is, I can show the AC source like C1, RS and Vs. If you want to show fixed biasing, you can show fixed biasing like this. Okay. So now when you form the AC model, then what you do is, when we form AC model, then we basically short circuit the capacitor. When we short circuit the capacitor, this is Vs. This RE gets short circuited. So RE or the emitter terminal becomes ground. Then you also ground VCC. If you ground VCC, then this C1, this RB gets connected between base and ground. We will make this ground. So RB gets connected here. Okay. Then this RC gets connected between collector and ground. And the collector terminal is connected to V0. Now what we'll do is, we'll replace the transistor by its H parameter model. If I replace the transistor by its H parameter model, then in the input loop, what I will do is, I am using the simplified hybrid model. That is, I am ignoring the early effect. So in the input loop, what I will do is, in common emitter configuration, I will show a resistance HIE, and in the output side, I will show a current source HFE IB. Okay. Then since we are ignoring the early effect, HOE will not be shown. Then between collector and emitter, this terminal is emitter, base, collector. Between collector and emitter, we have a resistance RC. This is your V0. This emitter will be grounded. Now see this, RC here acts as load on the circuit. And in the previous video, I told you the condition to ignore RHO. We can ignore HOE if HOE into RL, but here RL is RC is less than equal to 0.1. So you can ignore HOE if you know that HOE into RC is less than 1. Now if suppose, if we talk about the current gain, voltage gain and the input impedance. When we talk about input impedance, this is RI. The input impedance in this case is RB parallel HI. What about output resistance? The output resistance in this case is RC. Now what we need is the voltage gain, right? We need voltage gain. So for voltage gain, what you can do is, you can see that this current will flow like this. So plus minus. But V0 is opposite plus minus. So V0 is minus HFE IB into RC. Suppose if RS is 0. If this RS is 0, the voltage here will be Vs, which means IB can be written as Vs over HIE. So V0 is minus HFE by HIE RC Vs. So the voltage gain V0 by Vs is minus HFE RC by HIE. Now if you want overall voltage gain is simply voltage gain into, you can apply potential division, which is HIE by HIE plus RS. Because, sorry, not HIE actually. The effective resistance here is RI over RI plus RS. Okay. The effective resistance here is RI. So we will divide voltage between RS and RI. So you can write down as the overall voltage gain. Is it fine? So now what we'll do is, we'll take a look at the next circuit in which we have not bypassed this RE. So I am directly drawing the model. What will happen now? Suppose this is Vs. This is RS. Coupling capacitor will be shorted. Between base and ammeter, we will have an impedance HIE. This is base and this is the ammeter terminal. And between ammeter and ground, we will have resistance RE. Then between collector and ammeter, we will have a current source, which is HFE into IB. Again, if we ignore early effect, we will remove the HO. Now if you ground this VCC, then this RC will be connected between collector and ground. This is your collector terminal. So this RC will be connected between collector and ground. This is your V0. Now if you see that this HFE into IB current is going like this, that means the voltage here will be plus minus, this voltage will be plus minus. So you can simply write V0 is minus HFE IB into RC. Now the current here would be 1 plus HFE IB. So what we need here is, we need the parameters of this amplifier. So the first parameter that I am deriving is current gain. So the current gain is I0 over IB. Now I0 always goes from positive to negative terminal of V0. Okay, from positive to negative terminal. As you can see, I0 is going like this downwards, but this HFE into IB is going upwards. So you can write minus HFE into IB by IB is minus HFE. So the current gain of this amplifier is minus HFE. Then the next parameter that I am going to derive for you guys is the input resistance. Input resistance, always remember, is taken after. It is taken after RS. So Ri is Vi over IB. Now how to calculate this VI? It is the sum of voltage across RE and HIE. So VI is HIE into IB plus 1 plus HFE IBRE over IB. So it will become HIE plus 1 plus HFE into RE. So that will be the input resistance. Is it fine? Earlier in the previous case, the input resistance was RB parallel HIE, which is approximately HIE. Now it has increased. It has increased by this factor. So what you can say, by the use of RE, RI increases. Now the next parameter that I will derive for you is the voltage gain. I am talking about voltage gain and not the overall voltage gain. So the voltage gain AV, this voltage gain AV is V0 by VI. If I was talking about overall voltage gain, it will be V0 by Vs. So V0 is minus HFE IB RC. What about VI? VI we just now had written HIE into IB 1 plus HFE IB RE. Now IB will get cancelled out from numerator and denominator. So minus HFE RC by HIE plus 1 plus HFE into RE. That will be the voltage gain. Now this voltage gain is less than the earlier value. The earlier value was minus HFE RC by HIE. So you can say that voltage gain reduces due to RE. When we talk about overall voltage gain, it is written as AVS, which is V0 by Vs, which is equal to V0 by Vi into Vi by Vs. V0 by Vi is AV. Vi by Vs is obtained by potential division Ri over Ri plus Rs. Remember, this factor comes from voltage division. How? See, there is a source Vs. It is in series with a resistance Rs. And we replace the entire circuit here. The entire circuit here can be replaced by resistance Ri. And the voltage across this Ri is Vi. So that is how I have written this factor. Okay. That is your overall voltage gain. Is my point clear? Now if you talk about the output resistance, if you want to talk about the output resistance, how do we calculate the output resistance? The output resistance is simply, in our case, equal to RC. Okay. The output resistance will be this. So what you can say is, due to unbypassed RE, input resistance increases and the voltage gain decreases. These are the two factors that occur if your RE is unbypassed. But what is unaffected? R0 remains same and the current gain is also remaining same. The only thing that is changing is the voltage gain and your input resistance. Is it fine? Output resistance basically is not exactly same, but it remains almost same. Okay, you can say R0 almost remains same, but Ri increases by a large amount. So this type of theory question can also be asked to you. So I'll write, what are the effects of unbypassed RE? If I summarize it here, first of all, it stabilizes the Q point. I told you RE is used to stabilize Q point. Then you can say input resistance increases voltage gain, decreases current gain, remains same, and output resistance is almost same. Okay, so these are the effect if you don't bypass RE with a ammeter capacitance or CE. Okay, moving on, let us see another application of hybrid model. The other application is common collector amplifier. Now see here, it is also called as your ammeter follower. I told you why we call this circuit as ammeter follower, because V0 is connected to the ammeter terminal. Now see here, we have connected the source at the base, collector is connected to VCC, and we are taking output across RE. Now when we talk about hybrid model for CC configuration, common collector configuration I am talking about, then what happens? Then the input resistance will be shown using HIC. I told you the subscript represents the configuration. So for common collector it will be C, common base it will be B, and common ammeter it will be E. Then HRC VEC, HFC IB, and HOC. Since the collector is common, the input current will be IB and the output current will be IE. The input voltage will be VBC, the output voltage will be VEC. Remember, we use same model for all configuration as well as for PNP and NPN. We never change the AC model for NPN and PNP transistor, and also we use same model for all the configuration when we talk about hybrid model for common collector, common ammeter, and common base. Just we are changing the currents and voltages and the name of the parameters, but the circuit is same. So if you write down the equations here, VBC is HIC into IB plus HRC into VEC. Then IE is HFC into IB plus HOC into VEC. These are the equation. Now what we say is that if early effect is ignored, which parameters will be ignored then? Tell me. We will ignore HRC and HOC. And also, what is the condition for ignoring HOC? We say that if HOC into RE, because now RE is the resistance across V0. So RE acts as the load. So HOC into RE is less than equal to 0.1. We will ignore HOC and HRC. Okay. So these are the condition under which we ignore HOC and HRC. Now let me draw the model here. This is RS. This voltage is your VS. This terminal is grounded. Now between base and the collector, we will show HIC. This current is base current. Now you will ground this VCC for AC model. When you ground this VCC, this collector terminal gets connected to ground. This is base, this is collector. So collector terminal gets connected to ground. Then we have a current source HFC into IB. HO is ignored. Now see this. This terminal is ammeter. Ammeter has a resistance RE which is connected to ground. This is RE, and this voltage is V0. So this is the circuit. Now what parameters do I have to find out? I have to first find out the current gain. So I'll find in the next slide. So first I'll talk about the current gain AI. So this AI is actually equal to I0 over IB. Now see this current HFC into IB. It will be flowing like this. That is opposite to I0. So what I can say? I0 is minus HFC into IB by IB. That is minus HFC. Always remember, in common collector, the current gain is IE by IB, which is gamma, or you can say 1 plus beta, which means HFC is actually equal to minus gamma. Okay. Then the next parameter that I am deriving is your input resistance, RI. What I told you about input resistance? In input resistance we ignore RS. So input resistance is this one. So as can be seen from the circuit, I'll directly write input resistance is HIC. Okay. Is it fine? So that is your input resistance. Then the next parameter that I am deriving is your voltage gain. Okay. Voltage gain AV. For voltage gain, if we are only talking about voltage gain, we will take this as the input voltage. So voltage gain will be V0 by Vi, not V0 by Vs. V0, how can you write V0? The plus minus will be like this, but V0 polarity is opposite. So V0 can be written as minus HFC into IB into RE. That is your V0 by Vi. Vi is the voltage across this resistance HIC. So Vi is HIC into IB. So IB gets cancelled, minus HFC RE by HIC. That is your voltage gain. Okay. Now this can also be written as gamma RE over HIC, because HFC is minus gamma. This is greater than 0. So it means 0 degree phase shift. In common emitter, how much phase shift we get? 180 degree. In common collector we get 0 degree phase shift. Now if you want to find out the overall voltage gain, for overall voltage gain, what I have told you, we have to apply one potential division also. So we write AVS is equal to AV into input resistance by input resistance plus RS. So it is less than AV. That is your overall voltage gain. Then next we talk about output resistance. Output resistance, if you simply see from here, output resistance we see only there is one resistance connected across output, that is RE. Okay. So output resistance in our case becomes RE. Is it fine? We just have drawn the simple model and we have found that the output resistance is RE. So the biggest benefit of hybrid model is this circuit. This circuit remains same for all the configurations. So you don't have to think about the configuration. This circuit will remain same. Similarly, let us try and derive for another configuration, common base. If you see here, the input is applied between emitter and base. This is base, this is emitter. And output is taken between collector and base. So it is your common base. Again, The circuit will remain same, but the name of the parameters will change. Now we will use B in the subscript because it is common base. So HIB, HRB, HFB, HOB. Since base is common, the input current will be ammeter current, output current will be the collector current. Okay, input current is ammeter current and output current is collector current. Then the input voltage is VEB and output voltage is VCB. So this source depends on VCB, this source depends on IE. Remember again, the circuit remains same, but only thing that we have to do is the change the subscript in the parameter to indicate which configuration is it, and based on configuration we have to decide the input voltage, input current, output voltage, output current. That is totally dependent on the configuration. Now let me replace BJT by its equivalent circuit in this configuration. So what I have shown here is, this is RS, this resistance is RE. Now this terminal is ammeter. If I draw simplified model or I ignore early effect, then this is HIB and the current here is IE. Again what I am doing is, I am ignoring early effect in order to simplify the analysis. Now as you can see, this terminal will be base. Okay. Now between collector and base we have a current source. This current source is HFB into IE. Okay. Then you will short circuit this VCC. So between collector and base we will have a resistance RC, and then we will have the output voltage V0. Now see this. Actually when you have ammeter current IE, the collector current should leave. But here the collector current is entering. We know that IC over IE is alpha. Is it fine? But collector current should leave. Why it should leave? If ammeter current is entering, collector and base current must be leaving. So that means here this HFB is the current gain. It is minus alpha, because the direction of your current source should be such that collector current is leaving the terminal. Now let me derive parameters one by one. So the first parameter that I am interested in deriving is the input resistance. I told you when we are talking about input resistance, you ignore the source resistance. So this is your input resistance. As you can see, it is nothing but combination of two resistance in parallel. So it is RE parallel HIB. Then we talk about current gain. If we talk about current gain AI, I will write AI is I0 over IE. The input current here is IE. I am not talking about overall current gain. This current is IS. I am only talking about current gain. I0 is the current in RC. But if you see, the actual direction of current is from bottom to top, whereas I0 is top to bottom. So I0 can be written as minus HFB IE by IE, which is minus HFB. As I told you, it is alpha. So HFB is minus alpha. Then we talk about the next parameter, that is your voltage gain. Now if I were talking about overall current gain, I would have taken I0 by IS. But I am only talking about current gain, so I0 by IE. This voltage gain is nothing but V0 by Vi. Remember, not Vs. Vi is the voltage here. So V0 is nothing but minus HFB IE RC. Is it fine? Because plus minus based on current will be like this, but V0 polarity is opposite. If V0 polarity is opposite, I will use a minus sign. Vi, input voltage. If you see the input voltage is current multiplied by resistance. So HIB into IE. IE gets cancelled. HFB RC by HIB. When we talk about overall voltage gain, I told you in overall voltage gain what we have to do is we also have to use a potential division, which is AV into RI by RI plus RS. Okay, it is always less than the voltage gain AV. And the last but not the least parameter, that is output resistance. So if you see from the output side, what is the resistance that is visible to you? So the output side, we can see that output resistance is simply RC. Okay, as simple as that. So are you getting my point? The beauty of hybrid model is that the internal circuit for BJT remains the same, but these parameters, the name of these parameters will change. So what we have studied in this lecture, I have told you common emitter amplifier with unbypassed RE. Okay. Then I have told you common emitter amplifier with bypassed RE. In unbypassed RE, I have told you the voltage gain is less, the input resistance is high. Then we saw common collector amplifier, and at last we saw common base amplifier. So what we have observed is that the internal circuitry of hybrid model remains the same. No matter which configuration we are talking about, we just have to change the parameters being used in that configuration. Okay, so that will be all from this lecture. In the next video, I'll show you how to use this hybrid model to solve amplifier problems. So we'll solve some problems based on this hybrid model. Okay, thank you. Hi guys, in the previous two videos I have explained to use hybrid equivalent model of BJT, and what we saw in that model is the circuit remains same for all the configuration, and the only thing that changes is the name and the value of the parameters. So in this video I'll show you how to solve the problems based on hybrid equivalent model. So see the first question. It says calculate AI means current gain, RI input resistance, voltage gain, overall voltage gain, output resistance, and R0 dash means overall output resistance for a common emitter configuration. In this it has shown us the parameters. H parameters are given and two H parameters are 0, which means it is ignoring early effect. Okay, early effect is ignored in this circuit. So I'll try and draw the circuit. First what I'll do is I'll draw this Vs. Always remember this Vs will be a AC source. Then I'll draw this Rs. Now I have reached the base terminal. Remember this capacitor will be shorted because we are dealing with AC analysis. And the beauty of this hybrid model is that the first thing that I am keeping on telling you, that is the circuit remains same And the other thing is that you don't have to perform DC analysis. Why? Because H parameters will be directly given to you, so you can directly start with AC. Now we have reached the base terminal. Between base and emitter, we will have a impedance HIE, and the current in this HIE will be IB. Now this is our emitter terminal. This emitter terminal is grounded. Then we have collector. Between collector and emitter we have a dependent source HFE IB. Since HOE is 0, it will be open. Now see this RC. You will ground this VCC. If you ground this VCC, RC will be connected between collector and ground. So this is RC. This voltage is V0. Now let us see how to solve this problem. This current we call it as I0. The first thing that it is asking is the current gain. So current gain is nothing but I0 by IB. Now see this thing. What happens is I0 is in opposite direction to this. This current is from bottom to top. So minus HFE IB over IB. Okay. So HFE is how much? 50. So this current gain comes out to be minus 50. Okay. Now you guys might be thinking that why I have taken IB and not IS. So why I have taken IB and not IS is that if you see the circuit carefully, you will see that IS is the current leaving the source. Okay. If it is the current leaving the source, it is same as the current IB. See, if I show here IS is same as IB. If nothing is mentioned, always find out I0 by IS and not I0 by IB. Is it fine? The other thing, input resistance. We know that input resistance is always excluding RS. So this is RI. This RI input resistance is nothing but HIE, which is actually 1 kilo ohm. So the input resistance is 1 kilo ohm. Then what about voltage gain? If we are only talking about voltage gain and not the overall voltage gain, what I'll write? AV is V0 by VI, not VS. V0 is how much? I0 RC. VI is how much? HIE into IB. That is the voltage across this HIE. So I0 by IB. I0 by IB we just now calculated is minus 50. RC is 5 kilo ohm. And HIE is 1 kilo ohm. So it is minus 250. Okay. Moving on. The next parameter that it is asking us is overall voltage gain. That is AVS. So I told you AVS is obtained using the voltage gain into a factor of potential division, which is RI by RI plus RS. AV is minus 250. RI we just now calculated, it is HIE, that is 1 kilo ohm, and RS is 10 kilo ohm. So 1 by 1 plus 10, that is minus 250 by 11 minus 22.7. The next parameter that we have to calculate is the output resistance. If it is only talking about R0 and it is asking R0 dash separately, then this is the overall output resistance. So if you see here, we have ignored HO because it is 0. Then what we will say is R0 is the output resistance looking from here and R0 dash is from the V0 terminal. So if you look at this HOE, then what you will say is R naught is nothing but 1 by HOE, which is infinite. What about R naught dash? R naught dash, if you see, it is nothing but parallel combination of these two. So R naught dash is nothing but R naught parallel RC. R naught is infinite. So when you take infinity in parallel with something, it comes out to be RC. So it is 5 kilo ohm. So overall output resistance is 5 kilo ohm, whereas the ideal output resistance is infinite. Okay. But in the question, remember, when it only asks, in numerical, if it only asks voltage gain, you will find out AVS. If it only asks output resistance, you will find R naught dash. Now, if it says separately voltage gain and overall voltage gain, then you will find AV and AVS. Otherwise, if it only says voltage gain, you will always find AVS. You will never find AV. So whenever it asks any parameter, you always find out the overall parameter and not the internal parameter. Next one. So in this question it says, for a common ammeter configuration, find voltage gain AV, input resistance RI, and current gain AI. It is giving us the parameter HIE 1 kilo ohm, HFE 50, HRE and HOE 0, which means early effect is being ignored. Now whenever it only says the voltage gain, always remember you have to find the overall voltage gain. So let me try and draw the circuit. So first what I'll do is, I'll draw VS. Okay. Then I'll draw RS. Okay. But for AC model, we ground this VCC. If we ground this VCC, the top and the bottom terminal both are grounded, which means this 10 kilo ohm and 100 kilo ohm are in parallel. So we will have a resistance 10 parallel 100. Now we have reached the base terminal. We know between base and ammeter we have a resistance HI. This is your ammeter. Now ammeter is directly connected to ground. So ammeter is connected to ground. Between collector and ammeter we have a current source. This current source is HFE into IB. IB is this current. Then see this RC. RC is connected between collector and ground. So between collector and ground we have RC. Collector terminal is connected to V0, and see this I0. I0 is going from collector to ground. So I0 is going from collector to ground. So we'll derive all the parameters one by one. So first I am focusing on the input resistance. Now I have always told you input resistance is calculated after RS. That is, RS is not a part of input resistance. This voltage is VI. This current is II. So if you see, the input resistance is nothing but parallel combination of these two resistances. 10 parallel 100 parallel HIE. Okay. Which means how much will it come out to be? 10 parallel 100 is 100 by 11 in parallel with 1. 100 by 11 divided by 100 by 11 plus 1. So 100 divided by 111. Okay. So how much this resistance comes out to be? If you put in the calculator, it will come out to be 0.9 kilo ohm. Is it fine? So that will be the value of the resistance, that is 0.9 kilo ohm. Now what happens? The next parameter that I will derive is the voltage gain. For that I'll write V naught. V naught is I naught into RC. If you see, the actual current is going like this, opposite to I naught. So I naught is nothing but minus HFE into IB into RC. What about VI? VI is the voltage across 10 parallel 100 and HI. Both voltages VI, they are in parallel. So VI is nothing but HIE into IB. Now if I find out voltage gain, AV, AV is V naught over VI, that is minus HFE IB RC by HIE into IB. HFE is 50, RC is 5 kilo ohm, HIE is 1 kilo ohm. So minus 250. Then we calculate overall voltage gain. I told you, when only it asks voltage gain, always make sure that you find out overall voltage gain, which is computed using a factor of voltage division, that is Ri over Ri plus Rs. Ri we have just now derived, it is 0.9 kilo ohm. Rs in the question is 10 kilo ohm. Okay, so how much this comes out to be? 250 into 0.9 divided by how much? 10.9. So it will come out to be 20.642. Okay, and the last parameter is the current gain. When we talk about current gain, again find out overall current gain. How you will find out? IB, how you will write out using current division? II into 10 parallel 100 by 10 parallel 100 plus HI. That is the current division I have applied between this 10 parallel 100 and HI. And what about I naught? I naught is minus HFE IB. So if I write down here, I naught is minus HFE IB. IB I have written as II into 10 parallel 100 means 100 by 11 over 100 by 11 plus 1. So current gain, which is I naught over II, HFE is 50 minus 50 into 100 by 111. So how much will this come out to be? 50 into 100 is 5000 by 111 is 45. So minus 45.045. So that will be your current gain of this circuit. Is it fine? So what I have done actually is, I have just found out the ratio of output current and the input current. Moving on, in the next problem it says we have to find voltage gain, input resistance and current gain, where we know the hybrid parameters and HOE and HRE are 0. Again it means early effect is being ignored. So now how will I start? I'll again start drawing the circuit. So this is Vs in series with Rs. Now we have reached the base terminal. Between base and ammeter we show a resistance HIE. Then we reach the ammeter terminal. See, this ammeter terminal is directly connected to ground, and this Vs terminal is also connected to ground. Now we have reached collector. We know between collector and ammeter we have to show a current source HFE into IB, where IB is this current. Our HOE is 0, so it will be open circuit. Now you will ground this VCC, which means this RC is connected between collector and ground. RC. Okay. Now I2 is the current shown between ground and collector. So this will be I2. This is V0. Now one resistance is remaining, this R dash. R dash is connected between collector and base. So you will connect R dash like this. Let me assume that the current here is I dash. Okay. Now this voltage is Vi and this current is Ia. Now we have to find the parameters. So from the previous two problems, what is the major difference here? The major difference is this R dash resistance of 200 kilo ohm connected between base and collector. So now, first what I'll try and do is, I'll try and find the input resistance. Input resistance, how do you find out? Vi over Ii. Now how to find this Ii? Ii is basically sum of two currents, which is I dash plus Ib. Now this Ib is very simple. It is Vi over Hie. But what about I dash? I dash is nothing but it is Vi minus V0 by R dash. Okay. What about this current I2? The current here is HFE into IB. The current here is I dash. So you can say I2 is I dash minus HFE into IB. Now the thing is, when we are calculating the input resistance, I have to somehow eliminate. What I have to eliminate? I have to eliminate this I dash. I have to bring the entire equation in terms of IB, or you can say II, or you can say Vi. So I want I dash in terms of Vi. I don't want V0. So what you can say? V0 is nothing but I2 into RC, whereas if we write V0 is equal to I2 into RC, or you can say I dash minus HFE IB into RC. Okay. So if we know this, we can also write V0 as Vi minus I dash R dash from this equation. Okay. So I'll write on the next page, I'll write I dash minus HFE IB into RC. It is also equal to Vi minus I dash R dash. So from here what I can say is, if we collect the term I dash, RC plus R dash equal to Vi plus HFE RC into IB. IB is nothing but Vi over Hi. So which means I dash is how much? Vi 1 plus HFE RC over Hi over RC plus R dash. That means how much? 1 plus, now HFE is how much? HFE is given as 50. So 50. RC. RC is how much? RC is 5 kilo ohm and HI is 1 kilo ohm. 5 by 1. By RC, 5 kilo ohm plus R dash is how much? 200 kilo ohm. So it means Vi into 251 by 205 K. So 251 by 205 will be how much? It will come out to be 1.224, but due to kilo it will be milli Vi. Now if you want to find out input current, it is I dash plus IB. I dash is 1.224 milli Vi. IB is how much? Vi by HIE. HIE is 1 kilo ohm. So 1 upon 1 kilo ohm is 1 milli. So 2.224 milli Vi. So Vi over II is Ri. That is 1 by 2.224 milli. If you divide 1 by 2.224, you will get 0.4496 kilo. Okay, that will be the input resistance. So first parameter we have determined. Okay, so I'll be removing this. Then what I'll do is I'll try and find out the next parameter, that is the current gain, or let me solve it in the next slide. So the next parameter is your current gain. This data can be reused, that is why I haven't deleted. Now see, this current gain will be nothing but I2 over II. Okay. Now I2 is how much? I dash minus HFE IB, whereas II is I dash plus IB. So I dash is how much? 1.224 milli V1 minus HFE is how much? 50. IB is how much? Sorry, Vi. Vi over 1 kilo ohm, 1.224 milli Vi plus IB is Vi over 1 kilo ohm. So Vi will get cancelled. 1.224 milli minus 50 milli, because 1 upon 1 kilo ohm is 1 milli. 1.224 milli plus 1 milli. So it will be minus 48.756 by 2.224. So how much will this come out to be? 48.756 by 2.224, 21.922 minus. That is your current gain, I0 over II. Is it fine? Last, if I want to find out voltage gain, voltage gain will be, suppose V0 by Vi. V0 is I0 into RC. Vi is II into Ri. So that is your AV, but we will always find AVS. So AI, I0 by II, we just have calculate AI into RC over Ri. So AI is minus 21.922. RC is how much? 5 kilo ohm. Ri we just now calculated in the previous section, 0.4496. So how much will this come out to be? Current gain multiplied by 5k divided by 0.4496, that is 49.2821 minus 49.2821. Now if you want to find out the overall voltage gain, AVS will be AV multiplied by Ri over Ri plus Rs. So the voltage gain AV in this case is minus how much? 49.2821 into Ri is how much? 0.4496 by Rs is how much? 10 plus 0.4496. Okay, so this overall voltage gain will be very less. If you divide it by 10.4496, it will come out to be 2.12. Okay, that will be the overall voltage gain. Is it fine? So that is how you can try this problem based on the feedback. So what I have done for voltage gain, actually I naught RC by II RI, and I naught by II, if you remember, we derived it as the current gain, that is minus 21.922. Is it fine? So you can try problems based on this. You just have to replace BJT by its hybrid equivalent model. In that model, remember, the circuit remains same, only the parameter values are different, and parameter values will always be given to you in the problem, just like I gave you in each and every problem. Okay, so this will be all from this video, and we'll talk more about other model or the third model in the next video. Okay, thank you. Hi guys, up to now we have studied two models for BJT AC analysis or amplifier modeling. The first model that I told you was the T model, or I called it as the RE model, and the second model was the hybrid equivalent model, or you can say H parameters of a two-port network. Also, I told you earlier about one of the models called as Ebers-Moll model, that is the most general and the non-linear model, which is not generally used for amplifier modeling, because in amplifier we are biasing the transistor in active region. So the other three models, that is RE model, H parameter model, and the model that we'll be studying today, are only applicable for active region. Remember this thing. The three most prominent models that are being used for problem solving are only valid in active region, whereas the Ebers-Moll model is valid for all the four operating regions of BJT. But what is the major concern with the Ebers-Moll model? That the model is non-linear and it is a large signal model. So today we will be discussing about the third model that is generally used for BJT AC analysis, called as hybrid pi model. Okay. Now what is the best feature of this model is, this model is mainly used for AC analysis of BJT at high frequency. Okay. So when we will be studying frequency response, then I will be only using this model. So remember, this is mostly used at high frequency. In high frequency, we will show the resistance as well as the capacitance. We'll show both the elements, resistance as well as the capacitance. But this resistance, the resistance in the model, resistance of hybrid pi, can be related to either RE model or you can say H model. But capacitances you cannot relate, because till now we haven't used any capacitance. So the resistance part of this model can be correlated with the two models that we have studied so far, but capacitances I will introduce later on when we will be talking about the frequency response. Right now I won't talk about capacitance. So if you see the diagram on your screen, you can see that there are various elements that I have placed in this circuit. I'll discuss about each parameter one by one. First thing, this model I have drawn for the case of common ammeter, and that is why the input voltage I am showing as VBE and output voltage as VC. So first I'll talk about the resistance RB. RB is called as ohmic base spreading resistance. Now what does it mean? It means when we are creating a BJT, okay, when we are creating a BJT, we know that the base area is smallest, and we have to form a ohmic contact. Okay, this is your ohmic contact, Now since base area is smallest, the resistance of this ohmic contact is highest. This is simply rho L by A, where A is area of contact. Since area of base is less than area of emitter, sorry, not less than, equal to, actually much less than, which is less than area of collector, which means this RB is much greater than RE, which is greater than RC. So this is very high as compared to these two. So these two are ignored. When we talk about contact resistance, we'll only include this base resistance, okay? Because these two resistances RE and RC are very small, so we are ignoring them. We are only considering the base spreading resistance because the base area is smallest and its resistance is highest. The next parameter, if you see, is the resistance R pi. So R pi is base emitter junction resistance when the junction is forward biased. Okay, it is base emitter junction resistance, that is your R pi. It is actually equal to HFE by GM. Now what is this GM? GM is the transconductance that I taught when we were discussing the common emitter configuration. There I told the transconductance is defined as ratio of output current to the input voltage, which we found as ICQ by VT. VT is the thermal voltage. Okay. So that is your transconductance. HFE is the common emitter current gain, which is also equal to beta. So it is beta by GM. So that is your transconductance. Then the next resistance that you can see is R mu. Okay. This R mu connects the collector and the base terminal. Is it fine? So if you see, R mu is resistance between output and input terminal. Since it connects the output back to the input, so it works as a feedback resistance. Now this feedback appears due to early effect, which means again, if we ignore early effect, R mu will be ignored. This resistance is very high, of the order of mega ohm. So if someone tells you in the question that ignore early effect, you will open circuit the resistance R mu. Similarly, R naught. R naught is output resistance, which is again due to early effect. Okay. So R naught and R mu indicate early effect. Just like in hybrid model we were showing HR and HO. So HR and HO represented early effect. Similarly here R mu and R naught represent early effect. RB is the resistance of the base contact, which is high, and R pi is the resistance of emitter base junction. Emitter base junction behaves as a diode, so it is the resistance of emitter base junction in forward bias condition, and GM is the transconductance. Okay, this is the model that is most commonly employed for analysis of BJT. So all these parameters are important, but most of the times this R mu will be ignored on account of early effect, okay, which will simplify the model. So when we talk about simplified hybrid pi model, you can see that R mu has been removed. The input current is I pi and the IB, and the output current is IC. This basically is actually a dependent current source, that is GM V pi. So you can call it as voltage controlled current source. Is it fine? Because it is a current source and it depends on the voltage. Which voltage? V pi. and V pi is nothing but the voltage across the R pi resistance. Is it fine? Like when we were talking about the T model or the RE model, there the current source was beta IB. So it was current controlled current source because the current source was depending upon the current IB. Here the current source depends on the resistance voltage V pi. So it is voltage controlled current source. Is it fine? So now if you see the simplified hybrid pi model, we have R pi, GM V pi and R naught. And if R naught is high, you can also remove this R naught, and what we will be left with is a resistance and a current source, which is very similar to the RE model. What is the major difference? The major difference from RE model is the current source. There was beta IB, but here the current source is GM V pi. There it was current controlled current source, here it is voltage controlled current source. Is it fine? So now here if you see this, the total collector current, how you can write? It is VCE by R naught plus GM V pi, and in this circuit V pi is actually equal to VB. So we'll take a look at how to use this model, and I'll show you how you can analyze different amplifiers. So first let us see common emitter configuration. The circuit given here is directly the AC model of common emitter amplifier. So it is understood that we have done DC analysis. So the step 1 for this model, like in hybrid equivalent model, what I told you, that hybrid parameters will be directly given. You never have to do DC analysis. But in this model and the RE model, you have to perform DC analysis. Okay. In both these models, you will perform DC analysis. Then you will find out the collector current ICQ. So here you will find GM is ICQ by VT and R pi is beta by GM. These two parameters we need, and also you can find out R naught, which is VA by ICQ. So these parameters are derived from the DC analysis, and then they will be used for AC analysis. So now suppose I form the circuit, I will draw like this: VS, then RS, then we have reached the base terminal. If you have reached the base terminal, you will show the resistance R pi. So I am ignoring the resistance RB here, so I am directly showing R pi. This is your emitter terminal, and the voltage across this R pi is V pi. Now this emitter terminal will be grounded because this emitter is connected to ground. Then between collector and emitter, we have a current source GM V pi. Okay. Then you can show it is in parallel with a resistance R naught, which you can ignore if early effect is ignored. Then you can see between collector and ground we have a resistance RC, and this terminal is V0. So that is your AC model of the BJT. Now we'll derive one by one each parameter. So first I want to derive voltage gain. The voltage gain AV, not the overall voltage gain, will be V0 by V pi. Okay. Now how you can calculate this V0? This R0 and RC will be in parallel, and this current will be flowing like this. So V0 will have opposite polarity than what is indicated. Plus minus are like this, but we are getting opposite polarity. So V0 will be minus GM V pi is the current, and what is the resistance total? R0 parallel RC by V pi. So this voltage gain is nothing but minus Gm R naught parallel RC. That is the voltage gain. If R naught is high, then this is minus Gm RC. Okay. Because in case of very high resistance, R naught parallel RC will be approximately equal to RC. Then next thing that I can ask is the output resistance. I have told you time and time again that when you find out output resistance, you have to ignore the load resistance. Since there was no RL shown in the circuit, this R naught will be nothing but R naught parallel RC, which is approximately RC. Then next is the input resistance. Again in input resistance, which resistance you have to ignore? You have to ignore RS. So what is the resistance looking from this terminal? It is R pi. Ri is R pi. Next, last we will derive overall voltage gain. This overall voltage gain is computed from voltage gain by a factor of voltage division, which is Ri by Rs plus Ri. So AV is minus Gm RC, Ri is R pi over Rs plus R pi. So that will be your overall voltage gain. Okay. So it is a model which is very similar to your RE model. So you have to use the same sort of analysis when you are solving. Now let us see what happens if ammeter is not directly grounded and we have a resistance RE. I told you what is the purpose of this RE. This RE stabilizes your Q point of BJT. Okay. So again what I'll do is I'll draw the AC model of BJT. So this is Vs. This is Rs. Then we have reached the base terminal. We have reached here. Once we have reached the base terminal, what I'll do is I'll draw a resistance R pi whose voltage will be V pi, and this resistance will be between base and ammeter. Now see this, ammeter is connected to ground by means of a resistance capital RE. Then I will reach the collector. Between collector and ammeter, I will keep a current source Gm V pi. Then we can have R naught, but if R naught is high, it will be open circuited. Between collector and ground, we have RC. Only open circuit R naught if it is very high. Otherwise, don't open circuit it. This is V naught. Okay. So this is the AC model. Now what you have to do is you again have to find out each and every parameter. Okay. So first I will again start from the concept of voltage gain. Okay. So when I am talking about voltage gain, I will write V naught by V pi. Now how to calculate V naught? This current is going like this, plus minus, but V naught polarity is opposite. So V naught is minus Gm V pi RC. So the voltage here will not be V pi, it will be actually V in. What is V in? V in is the voltage of input terminal or base terminal with respect to ground. Earlier what was happening is, if you see this circuit, ammeter was directly ground. So the voltage of base terminal with respect to ground is equal to V pi. But now since ammeter is not directly connected to ground, V in is not V pi. V in is basically the sum of V pi and the voltage across RE. Now how to calculate this voltage? This current in R pi is V pi over R pi. These two currents will get added here. Gm plus 1 by R pi into V pi. So if you want to find out Vn, Gm plus 1 by R pi V pi plus V pi. Okay, that is I am adding these two voltages V pi and the voltage here. So V pi 1 plus Gm plus 1 by R pi. Okay, sorry, into Re. Because that is the current Gm into 1 by R pi. So for voltage you have to multiply it by Re. So V pi 1 plus Gm Re plus Re by R pi. Now if you take the ratio, V pi will get cancelled. So minus Gm Rc by 1 plus Gm Re plus Re by R pi. It is less than minus Gm Rc. Okay, don't consider this negative sign. I am just talking about the magnitude. So what we can say is, by introduction of this Re, the voltage gain has reduced. Okay. Next we will talk about the input resistance Ri. Okay, I am talking about input resistance Ri. So input resistance Ri is nothing but Vi over Ii. This Vi is V pi 1 plus Gm Re plus Re by R pi. Now this input current. See this input current. This is the input current. How much is it? It is V pi by R pi, and Vin I have written from here. So input current is V pi over R pi. So it will be 1 plus Gm Re R pi plus Re. So that will be the input resistance. Okay. Next we will consider the concept of output resistance. Now from the circuit you can directly see that this output resistance is nothing but Rc. Last parameter, overall voltage gain. So what I have told you about overall voltage gain? That in overall voltage gain we consider voltage division along with the voltage gain. So the factor of voltage division is Ri by Ri plus Rs, where Ri we have derived here. Okay, you can simplify this factor, not an issue, but remember it is nothing but voltage division into the voltage gain. Okay, so remember due to Re, input resistance increases. It has increased. And also what happens? Sorry, this will also be R pi. And also what happens? The voltage gain decreases. So these two things will always happen when you are introducing the ammeter resistance Re. Is it fine? Next, let us compare the three models that we have studied so far for BJT analysis. So this was the hybrid equivalent model. This is your hybrid pi model, and this one is your Re model. If you see, more or less all are same. So first let us consider this HIE. HIE here becomes R pi, here it becomes beta Re. So I will write HIE equal to R pi. R pi was how much? Beta by Gm. It is actually equal to 1 plus beta Re, which is approximately beta Re. Okay. So these three terms are same: HIE, R pi and beta Re. Then see this current source. HFE IB, beta IB and GM VB. This is current controlled current source. This is current controlled current source, but this is voltage controlled current source. So here HFE is actually equal to beta, whereas GM is ICQ by VT. Okay. Then this HOE. HOE represents actually the conductance. It is not resistance, but R0 is resistance. So HOE is nothing but 1 by RO. So all these three models are related to each other. So what you have to remember, when you calculate transconductance, it is ICQ by VT. When you calculate R pi, it is beta by GM, which is also equal to beta RE, which is also equal to HIE. And we know HFE equal to beta and HOE is 1 by R0. So that is the main relation between all the parameters that we have used in the three models of common emitter amplifier. So let me summarize what we have covered in this lecture. I have shown you the general diagram of hybrid pi model, and I have told you that this model is mostly useful at high frequencies. So this is the general diagram: base terminal, emitter terminal, then a dependent current source GM V pi in parallel with output resistance R0. Then this is the collector terminal. Okay. So the only difference is we are using a voltage controlled current source, whereas earlier we were using current controlled current source. Okay. That is the major difference. Earlier we were using this source as beta IB, now GM V pi. Is it fine? So remember this model, you can use any of the model depending upon the parameters given. If H parameters are given, always use hybrid equivalent model. But if no parameters are given and you want to use DC analysis, you can use the T model as well as the hybrid pi model. So in the next video, I'll show you some problems based on this hybrid pi model, and you'll understand how to approach such kind of problems. Okay. So this will be all from this video. Thank you. Hi guys, in the last lecture I told you about the hybrid pi model of BJT. So in this video what we'll do is, we'll make use of that model and I'll show you how to calculate amplifier parameters such as input impedance, output impedance and the voltage gain. Okay. So let us start with the first problem. If the transistor parameter are beta equal to 180, early voltage 140, transistor is biased at ICQ equal to 2 milliampere, find the hybrid pi parameter GM R pi R0 assuming VT equal to 25.9 millivolt. Now we know that the output resistance of BJT R naught is VA over ICQ. VA is the early voltage, that is 140. ICQ is 2 milliampere. So this ratio comes out to be 70 kilo ohm. Then we know that the transconductance expression GM is equal to ICQ over the thermal voltage VT, that is 2 milliampere by 25.9 millivolt. So it will come out to be 0.077 ampere per volt. And the last parameter R pi, that is the forward resistance of base emitter junction. It is beta by GM, that is 180 by 0.077, which will come out to be how much? 2.33 kilo. So these three expressions you always need to remember, and for using these expressions we need to perform DC analysis on a BJT, and then only we can find the amplifier parameter. Next problem, it says consider the circuit shown below. We know beta equal to 120, VT 25.9, VA equal to infinity. We need to find hybrid pi parameter and the small signal voltage gain. Now first of all, I will now perform DC analysis because ICQ is not given. If ICQ is given, we don't need to perform DC analysis. For DC analysis, we will short circuit AC source. So when we short circuit AC source, there will only be a DC source, then a 250 kilo ohm resistor, then we have a BJT, (5 volt) 4 kilo ohm. Now what I'll do is I'll apply KVL in this loop. So what I'll write, 2 minus this current will be IB into 250. Base emitter drop will be taken as 0.7. So IB will be 1.23 by 250 kilo ohm, that is 5.2 micro ampere. What we need is the Q point collector current, which is beta IB. So 120 into 5.2. Okay. So 120 into 5.2. So it will come out to be 0.624 milliampere. Once we have IC, I can calculate all the parameter. First of all, R naught, VA by ICQ. Since early voltage is given as infinite, this R naught is infinity, or you can say open circuited. Then the next parameter, GM, that is ICQ by VT, 0.624 by 25.9 millivolt. So this GM will be 0.024 ampere per volt. Then this resistance R pi, it is beta by GM, 120 by 0.024. So it will come out to be how much? 5 kilo ohm. Once we have all these parameters, what I'll do is I'll go to AC analysis. Now when we go for AC analysis, what we'll do is we will short circuit DC source. When we short circuit DC source, what we'll have is the AC source in series with the resistance. the resistance in series is equal to 250 kilo ohm. Then we have reached the base terminal. If you see, we have reached the base terminal. Between base and ammeter, we have a resistance which is equal to R pi. The voltage across this resistance is V pi. This is ammeter. Now see that ammeter is directly connected to ground. So ammeter is connected to ground. Then between collector and ammeter we have a current source GM V pi. This is collector. R0 is infinity, so it will be open. Then you will ground this VCC. When we ground this VCC, 4 kilo ohm is connected between collector and ground. So this 4 kilo ohm will be connected between collector and ground. And this voltage is V0. Now what it is asking us to find is the small signal voltage gain. So now see that the current GM V pi will be flowing like this, but V0 polarity is opposite. So what I'll write, V0 is minus GM V pi into 4 kilo ohm. What is this V pi now? V pi can be derived from Vs by voltage division. V pi is Vs into R pi by R pi plus Rs. R pi is how much? 5 kilo ohm, and Rs is given as 250. Okay, which means V0 is minus Gm into 4000 into 5 by 255 Vs, or you can say V0 by Vs. Gm we calculated just now, it was 0.024 into 4000 into 5 by 255. So it will come out to be 1.88. Okay, that is minus 1.88 will be the voltage gain, and if it is asking only the magnitude, you will write as plus 1.88. Okay, moving on. In the next problem it is saying, given that the amplifier has beta equal to 60, R0 equal to 20 kilo ohm, Vt equal to 26 millivolt, we need to find output impedance and voltage gain. Since collector current is not given, we will perform DC analysis. Okay, so when we perform DC analysis, we will open circuit the capacitor. If you open circuit the capacitor, how will the circuit look like? This is 220 kilo ohm, 2.2 kilo ohm. Now how you will apply KVL? You will apply like this. This current will be the base current IB, and this voltage drop here will be 0.7. So when we apply KVL, I write 12 minus 220 IB minus 0.7 equal to 0. So IB will be 11.3 by 220. Okay, and what about IC? IC will be beta IB, that is 60 into 11.3 by 220. Okay, so that means how much current will come? 3.08 milliampere. That will be the collector current. Based on this, we will find the amplifier parameters. First of all, R0 is directly given. We don't need to find it. So first of all, I will find GM. GM is ICQ by Vt. 3.08 milliampere by 26 millivolt. Milli will get cancelled. So this GM will come out to be 0.118 ampere per volt. What about R pi? R pi will be beta by Gm. So beta is 60 by 0.118. So how much will this R pi come? 508.47 ohm. So these are the amplifier parameter. Based on this, I will form the AC model. In AC model, when you are forming the AC model, what you will do? Short circuit capacitor and ground VCC, which is given as 12 volt. So what I will do is, I will short circuit the capacitor, so V in will be like this. Then we have reached the base terminal. Between base and ammeter, what I will show? R pi, which has a voltage V pi. Now this is ammeter terminal. Now see, ammeter is directly grounded. So ammeter is grounded. Between collector and ammeter, I will show a current source Gm V pi. This is collector. R0 is given as 20 kilo ohm. Always remember, never connect R0 with ground. It will always be in parallel with Gm V pi. Even if this is not ground, it will always be in parallel with Gm V pi. Next, let us talk about other resistances. If we ground this, then this 220 kilo ohm is connected between base and ground. So 220 kilo ohm is connected between base and ground. See this, this is collector, this is ground. So 2.2 is between collector and ground. Okay. Now this is V0. Now what we need to find is output impedance and voltage gain. Now see this. These two resistances are connected here and their lower terminal is grounded. So what you can say? They are in parallel. So what is the output resistance? Output resistance is 2.2 in parallel with 20 kilo ohm. So 2.2 in parallel with 20 kilo ohm, it will come out to be 1.98 kilo ohm. Now since this is 1.98, what I will do is I will remove this resistance and I will replace it by a single resistance here, 1.98 kilo ohm. Now this V0 is opposite. This current is going like this. So plus minus will be opposite to the given polarity. So V0 is minus Gm V pi into R0. Now as you can see, this 220 kilo ohm and R pi are in parallel. If they both are in parallel, you can say V pi is equal to V in, which means V0 by V in. V pi will get cancelled, minus Gm R0, and Gm we just now derived as 0.118 and R0 is 1980. I have converted it to ohms. So it will come out to be minus 234.87. Okay. That is the voltage gain of this amplifier is high. It is approximately 250, or you can say it is very high. We will now apply the same method to the third problem. It is saying consider an amplifier circuit shown in the figure. The transistor parameter beta is given, Vt is given. We need to now find input impedance and voltage gain. Again, collector current is not given, so I will perform DC analysis. For DC analysis, what we will do is we will open circuit capacitor. When we open circuit the capacitor, then this will be 10 volt, 372 kilo ohm, 4K, 10 volt. Okay, this is V0. Now when you are performing DC analysis, what you will do? First we will apply KVL like this. So what I will say? 10 minus 372 IB. Then base emitter drop 0.7. From this I can calculate IB as 9.3 by 372 milliampere. Now when you talk about collector current, it is beta IB, which is 9300 by 372 milliampere. So it will come out to be how much? This collector current will come out to be 2.5 milliampere. Okay. Now when you calculate GM, GM is ICQ by VT. ICQ by VT will be 2.5 milliampere by 25 millivolt, or you can say 0.1 ampere per volt. What about R pi? Beta by GM, which is 1 kilo ohm. Okay. So once we have the model parameters, and here if you see early voltage is not given. If early voltage is not given, consider it tends to infinity, which means R0 will also be infinite. So for R0, either it should give R0 or it should give us the early voltage. If not given, consider it to be open circuit. So now when we perform AC analysis, what we'll do? We short circuit capacitor and we ground the supply VCC. Okay. And we'll also ground this voltage. So now I'll draw the AC model. When we short circuit the capacitor, this is V in. The 372 kilo ohm resistor will now be grounded. Okay. Because this voltage is now grounded. We have reached the base. This is ammeter. This is collector. You will ground this also. When you ground this, 4 kilo ohm is between collector and ground. Between base and ammeter, first of all, I will show a resistance R pi whose voltage is V pi. This is your ammeter. Between collector and ammeter, I will show a current source GM V pi. Then this is your collector. Since R0 is not given, the R0 will be open circuited. Ammeter is directly connected to ground. And this 4 kilo ohm resistor is connected between collector and ground. This is V0. So the first thing that I need is the input impedance. If I need input impedance, what I'll say, input impedance is 372 kilo ohm in parallel with R pi. 372 kilo ohm in parallel with 1 kilo ohm. So it will approximately be 1 kilo ohm, but exactly it will be 0.9973. So you can also write it as 1 kilo ohm. Then the voltage gain. For voltage gain, if you see, the polarity of V0 is like this, but the current is flowing like this, which means plus minus will be opposite. So you can say V0 is minus GM V pi into 4 kilo ohm. Now since R pi and 372 are in parallel, V pi is V in. If you take the ratio V0 by V in, it is minus GM into 4000. GM is how much? We just now calculated. GM was, if you see, 0.1. So minus 0.1 into 4000, it will come out to be minus 400. Okay. That means the voltage gain is high and the negative sign indicates a phase shift of 180 degree. So that is how you can use this model also, or you can use RE model. You can use any model that you like, but remember, hybrid equivalent model will only be used when H parameters are directly given in the problem. Then only use the hybrid equivalent model. Otherwise, always make use of either RE model or the V pi model. Okay. So these two models can be used interchangeably, but at high frequencies, practically this hybrid pi model is only used. Okay. So this is all about the AC analysis of BJT From the next lecture onward, we will start the frequency response of BJT. Thank you. Hi guys. Hi guys, in the previous few videos I have told you about the BJT amplifier. We have seen different models of BJT amplifier like Ebers-Moll model, which was non-linear. Then we saw the T model or the RE model, then hybrid model, and then hybrid pi model. But the common thing in all those models was that we were only making use of resistances and the dependent sources. We were never considering any inductance or capacitance inside the BJT. But practically what happens when we talk about electronic circuits, then capacitances play a very important role. Similarly, when we talk about electrical circuit or the high power circuit, their inductances dominate. So you can't ignore these frequency dependent devices such as capacitance and inductance. These are also termed as parasitic, okay, because they are present inside the device, though they may not be desirable. So capacitances are mostly considered in the low power circuits or the electronic circuits, and inductances are always considered in the high power circuit or electrical circuit. So in this video what we'll do is we'll try and understand how does the gain of an amplifier vary when we vary the frequency of input signal. See, up to now what we were deriving is when we were talking about overall voltage gain. When we were talking about overall voltage gain, what we were doing? We were writing AVS is equal to V0 by Vs. It was coming out to be some constant term. But now what I will see is how this gain must be a function of omega, or it must be a function of frequency. So the variation of gain with the frequency of input signal is called as the frequency response. So when we talk about response, there are basically two types of response. One is called as time response. It means variation of output with time. That is, as the time changes, how the output will change. Similarly, when we talk about frequency response, what does it imply? It implies variation of output or gain with frequency of input signal. Okay, as the input signal frequency changes, the variation of gain is called as the frequency response. So as you can see, we have taken the gain in decibel. Now how do we take the gain in decibel? It is nothing but 20 log on the base of 10 mod AV. That is your gain on the scale of decibel. Then frequency is taken on log scale. That means it is not actually frequency, but it is log of frequency. Okay. So now you can see that there are three frequency ranges that we have specified: low frequency, mid frequency and high frequency. So whatever we have studied so far, there we had seen that the gain was constant. That means we were talking always about the mid frequency range, because in mid frequency range, if you see, the gain is constant. Okay. So someone might ask you in a question, if he wants to make it tougher for you, he might ask you, find the mid frequency gain or mid band gain. This mid frequency can also be called as mid band. Band means the band of frequencies or range of frequencies. So mid band gain does not vary with frequency. Mid band gain is always constant. But as you can see, at high frequency and at low frequency, the gain decreases as compared to mid frequency range. Now when the gain decreases by 3 dB, we call that frequency as the cutoff frequency. So the term cutoff frequency is also referred to as 3 dB frequency. Okay, that is the frequency at which gain at cutoff frequency is equal to gain maximum minus 3 dB. So when the gain reduces by 3 dB, we call that frequency as cutoff frequency. Now how it is defined is, see, suppose the gain becomes maximum gain by root 2, suppose. So 20 log maximum gain minus 20 log root 2. So this will come out to be 20 log maximum gain. 20 log root 2 is 3. That means where the gain becomes maximum by root 2, in dB it reduces by 3 dB. So you can also say if this gain is A, this is A by root 2. Okay. So at 3 dB frequency, the gain becomes 1 by root 2 times the maximum gain. Now why we have taken 1 by root 2 specifically? I told you that in AC, power is proportional to amplitude square. So when amplitude or gain becomes 1 by root 2, then power will become half. Okay. So this is also called as half power frequency. Are you getting my point? So when the gain reduces by a factor of root 2, in dB it is reduced by a factor of 3 dB and the power becomes half. So half power frequency, cutoff frequency, 3 dB frequency all mean the same thing. That is when gain becomes maximum gain by root 2. Now our focus in this section will be to understand what are the factors that are reducing the gain in low frequency and high frequency region, and how can we find out these cutoff frequencies FL and FH. Okay, this we have to understand. So next thing that we are going to study is the capacitances in the BJT amplifier. So I have showed you three capacitances, this CC1 and CC2. These are called as coupling capacitors or coupling capacitances. Always remember, these are external capacitances connected outside the BJT. Now what is the purpose of these two capacitances? The purpose of these two capacitances is to connect the supply to the amplifier and take the output from the amplifier. So these capacitances become short circuited in AC, and that is how the input signal and the output signal get connected to the amplifier. So if you have to define in one line, what you will say? Coupling capacitors connect the source and the load to the BJT amplifier. They are coupling the source and the load to the amplifier, hence they are called as coupling capacitor. Now I have told you about this CE also. I have told you in AC analysis we short circuited this CE. When we short circuited this CE, this resistance became short and gain became high. So this CE is called as ammeter bypass capacitor. Okay. Now the purpose of this capacitor is to bypass RE so that gain does not reduce. Otherwise RE acts as negative feedback which reduces the gain of the amplifier. Then the other two capacitances CD and CT. What we know is the Suppose we are talking about common emitter amplifier. This actually is common emitter amplifier because see, this is emitter terminal which is grounded. Input will be at base and output will be at collector. So in common emitter amplifier, the base emitter junction will be forward biased, right? And base collector junction will be reverse biased. Now in diode, I told you about two capacitances. In forward biasing, we talk about diffusion capacitance, and in reverse bias, we talk about junction capacitance. So that means for collector base junction, this junction capacitance is also named as transition capacitance. So that means the collector base junction is reverse bias, so it will have a transition capacitance, whereas base emitter junction is forward bias, so it will have diffusion capacitance. So this CD is the capacitance of base emitter junction, or you can say diffusion capacitance, whereas this CT is the junction or transition capacitance, and that is due to reverse biasing of collector base junction. So these capacitances are internal to BJT, whereas these three capacitances CC1, CC2 and CE, these are external capacitances that we have connected in the amplifier. So overall what you can say is there are 5 capacitances in the BJT, 3 are connected externally and 2 are developed internally. Now the question that comes to mind is, why does the gain reduce at low frequency? So always remember, at low frequency your CC1, CC2 and CE dominate. Okay. The transition and the diffusion capacitances do not dominate at low frequency. Now why is that? We know Xc is 1 by omega C. Now these capacitances are in the range of microfarad. So at low frequency Xc is moderate, because microfarad capacitance is considered as high capacitance. Okay, picofarad and nanofarad are low capacitances, but microfarad is high. So when you multiply omega into C, omega is low but C is high, so Xc will come out to be moderate, and that is why at low frequencies we have to consider these capacitances. Now why does the gain reduce at low frequency? The first reason is voltage drop across CC1 and CC2. These are connected in series. CC1 is connected in series with the supply. CC2 is connected in series with the load. Now due to voltage drop, V0 reduces. Now since V0 reduces, the gain which is equal to V0 by Vi, this also reduces. Okay, that is why the gain reduces at low frequency. The other reason is that CE does not completely bypass RE. Okay, if RE does not get short circuited, then it acts as negative feedback, and in negative feedback the gain reduces from its normal value. So if RE is not completely being bypassed, then the gain will definitely reduce due to negative feedback. Now how to decide which capacitances are to be considered in which frequency range? So basically we have 3 frequency range. We have low frequency, or you can call it as LF. Then we have mid frequency, which we can call as MF, and at last we have high frequency, which we call as HF. Okay. Then we have two types of capacitances. One were the external capacitance, which were coupling and bypass. I told you these are high capacitance. Then we have parasitic capacitance. Which are the parasitic capacitance? Diffusion and transition. These are low. They are in the range of picofarad. Now in low frequency range, always remember Xc is 1 by omega c. Now omega is low, capacitance is high, so it will be moderate. We will consider it. Now here C, capacitance is low as well as frequency is low, so Xc will be very high. If omega is low and capacitance is also low, their product will be low, but 1 upon their product will be high. High means it will be open. Is it fine? So if capacitance and frequency both are low, then it will be open. In mid frequency range, we short circuit the capacitor, which we were doing earlier, and we open circuit parasitic capacitance. Okay. Earlier I told you, when doing AC analysis, short circuit the capacitor, but I was never showing you the internal capacitances because internal capacitances were open circuited. What about high frequency? At high frequency this capacitance is high, omega is also high. So omega C will be very high. Omega is high, C is high, their product is high. So 1 upon product will be low. Low means short. But here omega is high and capacitance is low, so their product will be moderate. So we have to consider this capacitance. That means parasitic capacitances will be considered at high frequencies and external capacitances will be considered at low frequency. Okay. So when we will be studying low frequency and the high frequency response, we will only consider one kind of capacitances at a time. We will not consider all the capacitances simultaneously. Okay. So let us start. Now when we talk about the low frequency response, how was the low frequency response looking like? The low frequency response of BJT was something like this. If we only talk about low frequency, this was FL. Okay. It is similar to a high pass filter. Is it fine? I am not drawing the curve further. That is, I am not getting into high frequency range. I am talking about low frequency. So if you see only the low frequency curve, you will feel like it is a high pass filter. And that is why the circuit that I have given you, it is a passive. Passive means no active device. Passive first order high pass filter. Okay. Now in this case, if you want to derive the transfer function of this circuit, if we talk about transfer function, that is V naught S by VIS. It is equal to R. We are using potential division, divided by R plus 1 by SC. That is SCR over 1 plus SCR. That is your transfer function. Now you can go in the frequency domain. That is, you can write the gain as a function of frequency by replacing S by J omega. If you are only interested in magnitude of the gain, then this will become omega CR by under root 1 plus omega CR whole square. Or you can write it like this: 1 by 1 plus 1 over omega CR square. Now what happens is, as omega tends to infinity, this mod of gain will become 1. That is, at high frequency the gain is 1. As omega tends to 0, 1 by omega will be infinity. If denominator is infinite, the gain would become 0. That means at high frequency gain is high, so it is acting as high pass filter. Now this function is also written in this manner: 1 plus omega h by omega whole square, where this, omega L, where omega L is actually equal to 1 by RC. Now see, at omega equal to omega L, this factor will be 1. So gain will be 1 by root 2. And that is what I told you about the cutoff frequency. It is equal to the frequency at which gain becomes maximum gain by root 2. Here maximum gain is 1. So when gain becomes 1 by root 2, we will get the cutoff frequency. So that means in this case the cutoff frequency is 1 by RC. If it is 1 by RC, you can write it like this in hertz if you come. This is omega. Omega means angular frequency in radian per second. If we want to write in hertz, what I'll write? FL is 1 by 2 pi RC, and this is the cut off frequency. Why I have made this derivation is because I am comparing the low frequency response of amplifier to a high pass filter. Now if I know the cutoff frequency of high pass filter, in a similar manner I can derive the cutoff frequency of the amplifier. Are you getting my point? If I can derive a similarity between these two, then definitely I can figure out the cutoff frequency of the amplifier. Now see, in the numerator we have maximum gain. The maximum gain in amplifier is your mid-band gain. So what I'll say, the voltage gain is nothing but the voltage gain in mid frequency divided by under root 1 plus omega L by omega whole square. Okay, and that is the voltage gain at low frequency. So what is this mid gain? This is the maximum gain, or you can call it as the mid band gain, because we know the gain is maximum in the mid band region. Is it fine? So now we will see how we can utilize this knowledge in order to determine the cutoff frequency of the amplifier. Now what I'll deal in this section is the low frequency response. And as I have told you, in low frequency response or in low frequency region, which capacitances will be considered? CC1, CC2 and CE. And I have also told you, what I have told you, that the cutoff frequency is given as 1 by RC. That means if I know the capacitance, I just have to figure out the resistance and I can find the cutoff frequency. Before going that further, first I will derive the AC model of this common emitter amplifier. For AC model, what you will do is, now you will not short circuit the capacitor, because we want to see the dependence of gain on frequency. So we don't short circuit the capacitor. Is my point clear? Now always remember, when you will short circuit the capacitor, we will only short circuit the capacitor when we are talking about the mid frequency region. Without mid frequency, no capacitor will be short circuited. Okay, So capacitors are only short circuited in the mid frequency region. Now we are talking about low frequency, so we have to consider the capacitance, we cannot ignore it. Now we know in AC model we ground this VCC. If we ground this VCC, as I have shown you multiple times earlier, R1 and R2 will be in parallel between base and ground. This will be R1 parallel R2. Similarly, this collector resistance will be connected between collector and ground because VCC is now grounded. Then this CC2 is between collector and V0, and V0 is now connected to RL. Okay, like this. Now what we will do is we will replace this BJT by its small signal model. So if I draw that circuit also, so which model will I use? I will make use of the RE model. Okay, so I am redrawing the circuit with BJT being replaced by its model. Okay, in low frequency region you can use any model, but as I told you in the previous videos that at high frequency only we will make use of the hybrid pi model. This is your beta RE, this is IB. Then we will have a current source beta IB. Then we will have, actually this diagram is not completely correct because here I am not taking RE. Okay, so I'll draw it in the next slide, but what we'll do from now on, that I'll tell you here. We will only consider one capacitance at a time. See, there are three capacitances, which means it is a third order circuit. But the high pass filter that I showed you earlier only had one capacitance. It was a first order circuit. So in order to treat it as a first order circuit, what I'll do is I'll only consider one capacitance at a time and I'll figure out the cutoff frequency associated with that capacitance. How I'll find the cutoff frequency associated with that capacitance? Simply it will be 1 by 2 pi RC, or in radian per second you can call it as 1 by RC. Okay, but from now on I'll only consider one capacitance at a time. Is my point clear to you? So now for considering the effect of CC1, I'll replace BJT by its small signal model. But remember, when you are considering one capacitance at a time, the other capacitances will be short. Okay, other capacitances you have to consider as short circuit. This much is fine. Now see, what will happen is, first of all we are considering the effect of CC1. That means this CE will be short, CC2 will also be short. If CE is short, this RE becomes short and ammeter gets connected to ground. So if I draw the circuit again, this is Vs, then RS, CC1, this resistance was R1 parallel R2, this was ground. Then we had a resistance beta RE. Ammeter terminal will now be grounded. This current source was beta IB. where IB was the current in this beta RE. I will not consider R0. RC was the resistance between collector and ground. Since CC2 is shorted, it will be connected in parallel with RL. Now I have to find the transfer function V0 by Vs. For that I first need IB. So how you will find IB? First of all, what I'll say, this RC and RL are in parallel. If they are in parallel, what I'll do is I'll remove one resistance and I'll write here RL parallel RC. So this beta IB is flowing like this, but V0 is like this, which means plus minus polarity will be opposite to the V0 polarity. So V0 will be minus beta IB into RL parallel RC or RC parallel RL. Now we need IB in order to find the voltage gain. How to find IB? These two resistances are in parallel first of all, and this capacitance can be replaced by 1 by SC. So I'll first say R equivalent is R1 parallel R2 parallel beta RE. Then what I'll do is I'll apply voltage division. I'll try to find this voltage V. V is Vs into R equivalent by R equivalent plus Rs plus 1 by SCC1. Okay. Now once you have V, you can calculate IB. IB is nothing but V upon beta RE. That means Vs R equivalent by beta RE by R equivalent plus Rs plus 1 by SCC1. If you substitute this value in V0, what you will get? Minus beta IB, beta will get cancelled. Vs R equivalent by RE into RC parallel RL by R equivalent plus Rs plus 1 by SCC1. Once we have this value, we can calculate the voltage gain, that is V0 by Vs. So it is minus, how much will it come? R equivalent by RE into RC parallel RL into SCC1 if we take LCM, then 1 plus SCC1 R equivalent plus Rs. Now earlier we saw in high pass filter the transfer function was SRC over 1 plus SRC. So if you compare this, then you can say in the denominator the term with S represents the cutoff frequency. So you can say coefficient of S in denominator is cutoff frequency, which is omega L. Okay, because there, 1 by omega L, because there I told you that the cutoff frequency is 1 by RC. So here also what you can say from this expression, that the cutoff frequency will be 1 by R equivalent plus Rs into CC1. What was R equivalent actually? R1 parallel R2 parallel beta RE plus Rs into CC1. Okay. But there could have been a direct method to derive this expression. How? If you see, if I redraw this loop, if I redraw this loop here, I am short circuiting the supply. I am open circuiting this capacitor. This resistance was R1 parallel R2. This was beta RE. This was RS. Okay. Now if I ask you to find the Thevenin resistance across AB, if I want to find the Thevenin resistance across capacitor or AB, then what will be the resistance? It will be RS plus R1 parallel R2 parallel beta RE. That will be the resistance, and that is the same resistance coming in the denominator. So you can directly say it is 1 by RTH into CC1. That is, you have to calculate the Thevenin resistance across CC1 and then you can directly figure out the cutoff frequency. You don't always need to derive the transfer function. Is my point clear to you? You can either derive the transfer function and compare it with a high pass filter, but if you want to do it quickly, just find Thevenin resistance across the capacitor. Next, if I want to find the cutoff frequency associated with CE, in this case CC1 and CC2 will be shorted. So if I draw the circuit again using small signal model, this is VS, RS. Now I will short circuit CC1 and I will directly show the next resistance, R1 parallel R2. Okay, here there was CC1 which is now shorted. Then we have a resistance beta RE. The current in this resistance is IB. This terminal was ground, but this was connected to ammeter. This is base, this is ammeter. Ammeter had a resistance RE, in parallel to which we had a capacitance CE. Okay, since we are talking about CE, I cannot short circuit CE. Then we had a current source here, beta IB. I am not considering R0. This is your collector terminal. Between collector and ground, we have a resistance RC. Then we have CC2, but CC2 will be now short circuited. So I will directly show the load resistance RL. So again what I wish to find is, I wish to find the cutoff frequency associated with C. So first thing that I'll do is, these two resistances are in parallel, so they will be combined into one resistance, and that one resistance will be RL parallel RC. Now we can see that this beta IB current will be flowing like this. This is V0. But the polarity of voltage in resistance will be like this. Okay. So if it is like this, what I can say is that V0 is minus beta IB into RL parallel RC. But again I need the voltage gain or the transfer function V0 by Vs. For that I will change this capacitance into 1 by SC. That is, I am going into Laplace transform. So how to find this V0 by Vs? Okay, what should be the step? So what I will do is, suppose in order to simplify this, for simplification, just for simplification, what I am going to do is ignore RS. Okay. Suppose this RS is ignored. That is, I am short circuiting this RS. So Vs is the voltage here. That means the overall voltage here will also be Vs. First what I'll do is I'll combine these two resistance and capacitance into an impedance. So Z will be Re into 1 by SCE by Re plus 1 by SCE. That is Re by 1 plus SCE into Re. Now here the current is IB, here it is beta IB, so the current here would be 1 plus beta IB. Okay. So now we know the total voltage is Vs. Vs, if I apply KVL, like this, so what I'll say, IB, actually this resistance is not beta Re but 1 plus beta Re, which we approximate as beta Re, plus 1 plus beta IB into Z. That means 1 plus beta IB Re plus Z, or you can say IB is Vs over 1 plus beta Re plus Z. Now we know V0 is minus beta IB RC parallel RL. Beta and 1 plus beta are approximately equal, so it will get cancelled. So it is minus RC parallel RL over Re plus Z. That means the gain of the amplifier is minus RC parallel RL over Re plus Z. Z was Re over 1 plus SCE Re. Now if you take the LCM, what it will become? Minus RC parallel RL, okay, into what will happen? 1 plus SCE Re by Re 1 plus SCE Re plus Re. So this gain will become minus RC parallel RL 1 plus SCE Re upon Re plus SCE capital Re into small re. Now in the denominator I need a term something like 1 plus S into something. Okay, that is 1 plus S into something, that sort of a term is required. If that sort of a term is required, I'll take this common. Minus RC parallel RL, okay, 1 plus SCE Re are divided by Re plus small re whole divided by 1 plus SCE Re over Re plus Re. Okay. Now we know that by looking at the coefficient of S in the denominator, we can tell the cutoff frequency. So what I can tell is the cutoff frequency here is 1 by coefficient of S. The coefficient of S is CE into Re small re by Re plus small re. That is 1 by, this is capital Re in parallel with small re multiplied with CE. That is the cutoff frequency associated with CE. This you could have find directly again by finding the Thevenin resistance across this capacitor. How? I have told you, whenever whenever you want to refer the resistance from base to emitter, what to do? Divide by beta. If you divide by beta, it will become small re. It will be in parallel with capital Re. So the equivalent resistance across capacitor will be capital Re parallel small re. What I have said? Refer beta Re to emitter. When you refer it to emitter, it becomes from beta Re to Re. This Re is connected in parallel with capital Re. So this will be the Thevenin resistance across C. So remember, whenever you want to find the cutoff frequency, what you have to do? You have to find the Thevenin resistance across a capacitor, and once you do that, you can find out the cutoff frequency simply as 1 by RTh into C. So let us move on to our third capacitance, which is CC2. So if you see on the collector side, now I will find directly. If you see on the collector side, what we have is a current source beta IB. Okay, this terminal is emitter. But when you are studying CC2, CC1 and CE, they will be shorted. If CE is shorted, emitter is connected to ground. This is collector. We have a resistance between collector and ground, which is RC. Then we have a capacitance CC2. And this is V0. Across V0 we have a resistance RL. Now this both are grounded, so they both can be connected. Now if I ask you what is resistance across CC2, RTh across CC2. If I want to find that out, what I'll say is RTh across CC2 is RL plus RC, which means the third cutoff frequency that is associated with CC2 is 1 by RL plus RC into CC2. So that means here I have derived three cutoff frequencies, one using CC1. CC1 cutoff frequency that we derived was 1 by RS plus R1 parallel R2 parallel beta Re into CC1. The second cutoff frequency due to emitter capacitor, that was Re parallel small re into Ce, and this one is the third one. Now, but in your amplifier frequency response, I showed you only one cutoff frequency FL. Here we have three cutoff frequencies, omega L1, omega L2 and omega L3. So how we find FL? FL is the maximum of FL1, FL2 and FL3. FL means nothing but omega L over 2 pi. Okay. Now why I have taken maximum C? If there is one function like this which is passing everything above 10, then there is another function which is passing everything above 15. If I ask you, if we use these two systems, which frequencies will be passed? You will take the intersection. So one system is saying frequency must be greater than 10, other is saying frequency must be greater than 15. If you take the intersection, what you will get? Frequency greater than 15. That means when we have FL multiple values, we consider only the maximum out of all those values. So your lower cutoff frequency will be the maximum of the three frequencies that you have derived. Okay. Moving on to the last term in the low frequency response is called as unity gain frequency. Just now we have seen that the low frequency gain is given by mid frequency gain divided by under root 1 plus omega L by omega whole square. Or if you replace omega as 2 pi f, 2 pi will get cancelled. It can be 1 plus FL by F square. Now unity gain frequency means frequency F equal to Ft at which this gain becomes 1. The frequency at which the gain is 1 is called as unity gain frequency. This is AV mid over under root 1 plus FL by Ft whole square. Now if I say FL by Ft is much greater than 1, then you can say 1 equal to AV mid divided by FL over Ft, which means this Ft will become FL over AV mid. Okay, this frequency is called as your unity gain frequency. So no need to remember anything. Unity gain frequency is nothing but the frequency at which gain becomes 1. So if I summarize what we have learnt in this video, that when we talk about low frequency response, in that which capacitances are considered? CC1, CC2 and CE. Then in high frequency response, which capacitances are considered? Diffusion capacitance and transition capacitance. And how to find cutoff frequency? 1 by 2 pi into RTH into C. RTH is Thevenin resistance across C. So I told you we derived 3 cutoff frequencies, FL1, FL2 and FL3. Then FL is taken as maximum of the 3 cutoff frequencies. So what you have to do? Always remember, design the small signal model including the capacitances and find Thevenin resistance across each capacitance. But consider only one capacitance at a time. After doing this, you can find the 3 cutoff frequencies and the maximum of that will be your overall cutoff frequency. Okay, this you have to remember when you are dealing with the low frequency response, or you can say coupling and the bypass capacitor. Okay, so in the next video I will tell you about the high frequency response. Thank you. Hi guys, in the previous video I introduced to you the concept of frequency response of an amplifier. In that I showed you the general shape of the frequency response. The general shape of the frequency response was something like this. Okay. There I told you we divide it into three regions. One is the low frequency range. Then the second, in which the gain is almost constant, is mid frequency. Then high frequency. Then I told in low frequency range which capacitances we have to consider. We have to consider the external capacitances, which are the coupling capacitor and bypass capacitor. Similarly, when we talk about high frequency range, which capacitances do we have to consider? The diffusion and the transition capacitance. Then I told we have to figure out these cutoff frequencies FL and FH. So I told you FL is basically maximum of the three cutoff frequencies FL1, FL2 and FL3. FL1 was 1 by 2 pi the Thevenin resistance across CC1 into CC1. FL2 was 1 by 2 pi Thevenin resistance across CE into CE. FL3 was 1 by 2 pi Thevenin resistance across CC2 into CC2. We derived that RTH1 was coming out to be RS plus R1 parallel R2 parallel beta RE. Similarly, RTH2 we derived RE parallel capital RE, and RTH3 was RC plus RL. So these all derivations we covered in the last lecture. So I have told you how to analyze the low frequency response of BJT. So in this video our focus will be on the high frequency response. Now if we only draw the high frequency response of BJT without considering the low frequency region, then the response is something like, okay, this is your mid band gain, then the frequency at which the gain becomes 1 by root 2 times is FH, or your cutoff frequency. I told you cutoff frequency is also known as 3 dB frequency, half power frequency. This is your FH. Okay. Now if you see this graph resembles the graph of a low pass filter. That is why the circuit that has been drawn here is an example of passive low pass filter. Why I am calling it passive? Because there is no active component such as an op amp or a BJT. Now if you want to find the transfer function of this circuit, it will be V0 by Vi. We can find out V0 by Vi by voltage division, that is 1 by SC over R plus 1 by SC. So it is similar to 1 by 1 plus SCR. Now if you want to go into gain or frequency domain, you will replace S by j omega. So 1 by 1 plus j omega CR. In that, if you calculate the magnitude of gain, it will come out to be 1 by under root 1 plus omega square R square C square. Okay, that will be the magnitude of gain. Now in this, if you check at omega equal to 0, the magnitude of gain is how much? 1. At omega equal to infinity, the magnitude of gain is how much? It is 0. So that means it is behaving as a low pass filter because gain at low frequency is high, whereas gain at high frequency is low. Now this function can also be written as like this: 1 plus omega by omega h square, where omega h is nothing but 1 by RC. Now see, when omega equal to omega h, what will happen? It will be 1. So gain will be 1 upon root 2. That means omega h is the cutoff frequency. So you can say that the magnitude of gain is 1 over under root 1 by 1 plus omega by omega h square. And then you say that at omega equal to omega h, magnitude of gain is 1 by root 2. That is maximum by root 2. So omega h is cutoff frequency. So if you see the cutoff frequency here also it is same. It is 1 by RC. That means the method to derive the cutoff frequency will also remain same. We will derive the Thevenin resistance across the capacitor and then 1 by RC will give us the cutoff frequency. We can write down FH is 1 by 2 pi RC. Okay, that much is clear to you. So in this video, what our focus will be on analyzing the high frequency response and finding the upper cutoff frequency, that is FH, which is also equal to 1 by 2 pi RC. So for an amplifier, if I talk about, I will write AV, that is voltage gain at high frequency, will be equal to maximum gain. Maximum gain is observed in mid frequency region divided by under root 1 plus omega by omega h square. Now if you write omega equal to 2 pi f, that factor of 2 pi will get cancelled. So 1 plus f over fh whole square. Okay. So that is how the gain will vary in the high frequency region, and based on this analysis we will try and determine the upper cutoff frequency. But the question that comes to mind is, why does the gain reduce at high frequency? As I have told you, at high frequencies, we consider the low capacitances of the range picofarad. These low capacitances are also called as parasitic capacitances, which means they are undesired but they are present internally to the BJT. Now, what capacitances are these if I show in the BJT circuit? In BJT, base emitter junction is forward bias. So in a forward bias diode, we define a diffusion capacitance. Then we have a lead capacitance. Then we have a wire capacitance. Okay. Lead capacitance means capacitance of the terminal that is brought out from the BJT. Wire means the wire, copper wire or any other material which is used to connect BJT to other component. Remember, these are two different things. When you buy a BJT, as I showed you in the first lecture itself, the BJT has 3 terminals like this. These are called as leads. Now you will connect wires to these leads in order to connect BJT in a circuit, and that capacitance will be the wire capacitance. So lead capacitance is the capacitance of terminals that are brought out from the BJT. Wire capacitance is the capacitance of the wire used to connect BJT in a circuit. Similarly, between collector and ammeter also, we will have lead capacitance, we will have wire capacitance, we will also have the load capacitance. Load capacitance means the capacitance of load connected at the BJT. Now suppose BJT is driving another BJT. Okay, suppose I have connected 2 BJTs. So if BJT is driving another BJT, the input capacitance of the second will work as the output or the load capacitance of the first. Okay. So it means the load capacitance is nothing but the input capacitance of the second stage connected at the output of this BJT, because there can be multiple stages. Now we know base collector junction is reverse bias. That is why between base and collector we will show another capacitance, transition capacitance. Okay. Now this wire and lead capacitance are called as stray capacitances. That is, their location is unknown but they are present. And this CD and CT, these are parasitic capacitances. These are present internally to the BJT. Due to these capacitances, the gain reduced at high frequencies. They will reduce the value of gain. But we will not consider these stray capacitances. We will only consider the internal or the parasitic capacitance. But remember, practically these capacitances are also a part of circuit. Now before going any further, we must study about one network theorem that will help us in the high frequency analysis, that is called as Miller's theorem. Now what is the purpose of Miller's theorem? If any impedance is connected between two ports of the network, that is, I told you BJT is a two-port network. It has two ports, one is the input port and the other is the output port. It is very easy to analyze if input and the output ports are not connected together. The circuit is very simple. But what happens when any impedance is connected in between the input and the output port? The analysis becomes typical. Now to simplify that analysis, we use Miller's theorem, which can resolve that impedance into two impedances, one connected at the input port and the other connected at the output port. So what is the purpose of Miller's theorem? It is used to resolve an impedance connected between two ports into two impedances, one connected at the input port and other connected at the output port. Okay. So let us see how this is done. So if I say that this current is I, so how you will find I? I will flow from high voltage to low voltage, that is V1 minus V2 by Z. Now by KCL, I1 is also I, but I2 is minus I, which means V2 minus V1 by Z. Now when you want to break this Z into two impedances Z1 and Z2, then Z1 is connected only across V1 and Z2 is only connected across V2. So I'll say, suppose V2 by V1 is the voltage gain. Let me call it as AV. This is the voltage gain. So what I can say is, I1 is V1 minus AV into V1 by Z, which means V1 1 minus AV over Z, or you can say V1 over Z upon 1 minus AV, or you can say V1 by Z1, which means the impedance when referred to the input port, it will become Z over 1 minus AV, where AV is the voltage gain. Similarly, in the second part, I2 is V2 minus V1. But when you refer it to port 2, when you make Z2 is only connected across V2. So in this expression, I only want V2 and not V1. So I'll write V1 as V2 by AV. So you can say V2 1 minus 1 by AV by Z, or otherwise you can simplify it. You can write it like this: I2 is equal to V2 over Z upon 1 minus 1 by AV, or you can say V2 by Z2. So now if you see, I have done nothing. I have just compared the current in the two circuits and based on that I have found out the equivalent impedance connected at the input and the output port. So at the output port, what will be the impedance? If I write down Z2, if you want to write down Z2, what will be Z2? Z2 will be Z over 1 minus 1 by AV. Okay. So these are the equivalent impedances when they are referred to the input and the output port. Now this theorem, as I'll show you later on in this video, will be very helpful when we are analyzing the high frequency response of BJT. Similarly, we have another theorem, that is the dual of Miller's theorem. Now see, here again there is an impedance, but it is now lying between two currents, not between two voltages. I want to refer this impedance again separately to port 1 and port 2. For that, I will first write the KVL equations here. Suppose this voltage is V13, this voltage is V23. I want to apply KVL here. I will write V1 equal to V13 plus I1 plus I2. The current in impedance Z is I1 plus I2 Z. Now if I say that the current gain of this amplifier is AI minus I2 by I1. Why minus I2 by I1? Because current must enter one of the ports and it must leave the other port. So I2 should be actually leaving, but we have shown it entering. So I am showing a minus sign, minus I2 by I1. So if you want to refer it only here, only at the port 1. So what you will write the equation here? V1 is I1 Z1 plus V13. This is V13. So I only want I1. I don't want I2. So what I'll do? I will replace I2 in terms of I1. AI I1. So you can say V13 plus I1 Z 1 minus AI. If you compare these two equations, you can directly say that Z1 is Z into 1 minus AI. Now similarly, if you apply KVL here, you will say V2 is V23 plus current in impedance Z is I1 plus I2. But here if you apply KVL, this voltage is V23. You will write V2 is, current in Z2 is now only I2. So in this equation I only want I2. I don't want this I1. So what I will do is, I will replace I1 in terms of I2. I1 is minus I2 by AI plus I2. So you can write it like this, V23 plus I2Z 1 minus 1 by AI. Now compare these two equations. You can directly see that Z2 is Z into 1 minus 1 by AI. Okay. So that is called as the dual of Miller's theorem. Earlier we were dividing by this factor. Now we are multiplying. That means if impedance is connected between the two currents, you have to multiply this factor. But if it is connected between two voltage, you have to divide by this factor. So that is how dual is defined. But this dual will not be used anywhere in our analog electronics. We'll only make use of the Miller's theorem. So Miller's theorem is nothing but a network theorem which helps us in simplifying the analog network. Now, as I told you earlier as well, when we are talking about high frequency, at high frequency, which model is used? We only used hybrid pi model. Now in this model, what modification has been done? We have now introduced capacitances also. See, RB, let me revisit that for you. I told you earlier RB was base spreading resistance. Okay. I told you this is the resistance of the ohmic contact Since base area is smallest, this resistance is largest. RB dash E. I told you this is the forward bias resistance of base emitter junction. We can write its value also. RB dash E is beta RE, or you can say HFE by GM, or you can say it is R pi. Okay, that is your RE basically. RB dash E. Now this RB dash C, this was R mu. It represented the early effect. Okay, RB dash C is nothing but R mu. R naught, it was output resistance. It is also due to early effect. Other than this, VB dash E was actually V pi. So this current source is nothing but GM V pi. So I have added two capacitances. CD is your diffusion capacitance. Since base emitter junction is forward bias, we will consider diffusion capacitance for that junction. Collector base is reverse bias, so we will consider junction or transition capacitance for collector base junction. Okay. Now this is base emitter, this is emitter. So between base and emitter diffusion, between base and collector we have transition. Is it fine? So it is nothing but the hybrid pi model that we have studied earlier, but I have now introduced the capacitances. Now this model is also known by a name of a scientist. It is called as Giacoletto model. Okay, this is another name given to the hybrid pi model. Now what I wish to do in this slide, what I wish to try is deriving the parameters of this hybrid pi model in terms of your H model. Okay, but in H model we don't have any capacitances. So let me remove the capacitances and redraw this circuit. So what I'll do, I'll open circuit this capacitance. Why open circuit? These capacitances are very low, so their reactance would be very high, hence they will be open circuited. Okay. This is R naught. I'll now write it as R mu. I'll write it as R pi RB. Okay, simple notation. Now I want all these parameters in terms of the hybrid parameters or H model. Now in H model what we say is VBE is IB into HIE plus HRE VCE. Then we say IC is HFE IB plus HOE VCE. So what I can say is HIE is nothing but VBE upon IB when VCE equal to 0. VBE upon IB when VCE equal to 0. This is your IB, this is your VBE, this is your VCE. Okay. Now in this case, if I want to derive HIE, if I want to derive HIE for the circuit that I have drawn, what I have to do is I have to short circuit VCE. If I short circuit VCE, R0 will go away, R0 will be shorted. The current of this current source will pass through short circuit because current wants to have a path of minimum resistance. Then this R mu gets connected in parallel to R pi Y. See this path like this. It gets connected in parallel to R pi. So what you can say, HIE, which is the equivalent impedance VBE upon IB, will be how much? RB plus R pi parallel R mu. Now we know that R mu is very high in mega ohm. So it is simply RB plus R pi, which means you can write down RB as HIE minus R pi. I told R pi was nothing but beta Re. Okay. So we know the value of R pi. We can calculate RB using the H parameter, that is HIE. So I'll rewrite the equations here. We wrote HIE IB plus HRE VC, HFE IB plus HOE VC. So the next parameter that I'll try and use is your HRE. So how you will find out HRE? HRE is nothing but VBE over VCE when IB is 0. Okay, VBE over VCE when IB is 0. So let me redraw the circuit here. The circuit of Giacoletto model without capacitances. This is your VCE. This is R naught, R mu, R pi, RB. And this voltage is VBE. So we need to keep this IB equal to 0. That means what I can say here is, if this current is I, this current will also be I. Okay. So if we apply KVL here like this, so what you can say, VCE is I R mu plus R pi. R mu and R pi will be in parallel. This will be GM V pi. Now V pi is the voltage here. Okay. So basically V pi is how much? VBE, because there is no voltage drop across RB, which is equal to I R pi. So that means if you want to calculate VBE by VCE, that is HRE, it will be R pi over R mu plus R pi. That means if you take the reciprocal, it will be 1 by HRE, and you can find out R mu from here. It will be R pi 1 by HRE minus 1. So that is the value of your early effect resistance R mu. Okay. The last resistance that is remaining, we know R pi, we have computed R mu, we have computed RB, we need R naught. For R naught, what I will do is, I'll make use of this parameter HOE. So I am removing this computation and I'll redo for the next parameter. Okay. So what I am trying to do is, I am trying to relate the hybrid model with the Giacoletto model. So now if I write down HOE, what I'll say, it is IC over VCE when IB is 0. This current is basically IC. So we just now saw what is VCE. VCE was nothing but I into R pi plus R mu. Okay. Even now also IB is 0. So what about IC if you apply KCL? It is VCE by R naught plus GM V pi plus I. I have just applied KCL. Now VC is nothing but I R pi plus R mu over R naught. V pi. How to calculate V pi? V pi is nothing but I into R pi plus I. So if you now take IC by VCE, first let me simplify IC. r pi plus r mu over r naught plus gm r pi plus 1. So now if you take IC by VC, HOE, take ratio IC by VC, what it will become? R pi plus R mu over R naught plus GM R pi plus 1 whole divided by R pi plus R mu. So now from here, if you want to calculate R naught, what I'll have to do is, I'll have to simplify this. So I'll do HOE into R pi plus R mu minus GM R pi minus 1 is equal to R pi plus R mu by R naught. So R naught is nothing but R pi plus R mu by HOE R pi plus R mu minus GM R pi minus 1. So that will be the value of your output resistance R naught. So in this manner, what I can do actually is, I can correlate the parameters of the hybrid equivalent circuit and the hybrid pi model or the Giacoletto model. Okay, but you don't have to memorize these things. These values will be given in the examination. Now let us understand how to find the common emitter short circuit current gain. Short circuit current gain means when output is short circuited. So let me redraw the circuit, then you will understand how we have derived this circuit that I have drawn. The actual circuit was like this. RB, RB dash E, which was R pi. Then the diffusion capacitance CD. Then we had RB dash C, which is R mu. In parallel to this, we had transition capacitance CT. Then we had a current source GM VB dash E or GM V pi. Then we had in parallel to this a resistance R naught. And now what I have done is, I have short circuited the output. Now once we have short circuited the output, then what happens? Then this R naught is useless. And also one more thing that is happening is that this R mu is coming in parallel with RB dash E. Similarly, this CT is coming in parallel with CD. So that is why where I have drawn this circuit, this resistance RB dash E, this actually is RB dash E parallel R mu, which is approximately RB dash E, because this resistance is very high. Also we have ignored the value of RB. Base spreading resistance has been ignored. Since this CD and CT are in parallel, this is written here. So this is not CC, this is CT. They are in parallel, so they are directly added. Is it fine? Now I want common emitter short circuit current gain, that is I naught by II. That is, I want to find the current in short circuit divided by the input current. I want this ratio. Okay. Why I want this ratio basically is to find some important parameter that I'll tell you later. So see, from the circuit you can say I naught is minus GM VB dash E. Okay. What about II? II will be the sum of two currents. One is VB dash E by RB dash E. The second is VB dash E over the impedance of capacitance CD plus CT. Okay, 1 by SC. Capacitance is always 1 by SC. Now if you take the ratio I naught over II, VB dash E will get cancelled, minus GM divided by 1 over RB dash E plus 1 over S into CD plus CT. So this will become minus GM, if we take the LCM, SCD plus CT RB dash E over RB dash E plus S CD plus CT. Okay, that is the value that I am getting. Now, how to simplify this? Okay, how you can simplify this? You can simplify this by first of all writing CD plus CT equal to C. Okay, that will simplify a lot of effort. So this current gain will be minus GM S C RB dash E by RB dash E plus S C. Is it fine? So now what you have to do in order to reduce it to the standard form, divide this entire expression by SC. So what you can do is, this will be minus GM RB dash E. If we divide it by SC, 1 plus, 1 minute, am I committing some mistake? Because SC will be admittance. How is it getting added up here? Okay. Sorry. This will not be, this is a small mistake that I committed here. Okay. So basically it will be S CD plus CT. Okay. So if that is there, what I'll do is, I will just now substitute that S into CD plus CT will be SC. I am replacing this by C. So take the LCM. It will be 1 plus SC RB dash E. Now we just now saw that the transfer function, of low pass filter was something like 1 by 1 plus SRC. We told that 1 by RC is the cutoff frequency. So here also you can find out the cutoff frequency and you can write it. It is 1 by RB dash E into C. That is your upper cutoff frequency, just by comparing it with the low pass filter that we studied earlier. Now we have to talk about one important parameter, that is the unity gain frequency. So we have derived the current gain minus GM RB dash E over 1 plus SC RB dash E. Now you can go into into J omega. So minus GM RB dash E 1 plus J omega C RB dash E. I told you unity gain frequency is what? The frequency at which gain is 1. So calculate the magnitude of gain. Minus will go away when we take the mod. Divided by under root A square plus B square. Now I want a frequency. I want a frequency at which mod AI is equal to 1. So I'll keep it at 1. GM RB dash E by under root 1 plus omega T C RB dash E whole square. Okay, that will be the relation. Now what I will do is, I will try and simplify by squaring both sides. GM square RB dash E square is 1 plus omega T C RB dash E whole square. Okay. Now if 1 is very small as compared to the term on the right hand side, you can say GM square RB dash E square is omega T square C square RB dash E square. This gets cancelled. So omega T is simply GM by C. Okay. Now this GM, or you can say this C, is nothing but CD plus CT. That is diffusion plus transition capacitance. Remember, this formula is very important from numerical point of view. You will see many questions based on this formula only. That is, it will ask you to find the unity gain frequency. It is simply Gm by total capacitance, which is diffusion plus transition. Now let us see what if we don't short circuit the load but we connect a resistive load RL. Now this is the input port, this is your output port. Now if you see that these two parameters are connected between input and output. And I told you, whenever any impedance is connected between input and output, the analysis is difficult. So what we do? We use Miller's theorem. Why we use Miller's theorem? We use Miller's theorem to resolve that into an input impedance and an output impedance. Now this G means conductance, but we can also show resistance. No need to show conductance. This is CD. Now see, when you resolve this R mu, when R mu will come at the input port, how you will resolve it? It will be R mu divided by 1 minus voltage gain. Okay. But when we talk about capacitance, we saw Z input is Z over 1 minus AV, Z output is Z 1 minus 1 by AV. Now in case of capacitance, Z is 1 by omega C. So what you will write? 1 by omega Ci is 1 by omega C mu 1 minus AV. So you can say Ci is C mu 1 minus AV. C mu, or you can say it is, instead of mu you can write T, transition capacitance. So this capacitance here will be Ct into 1 minus AV. Resistance is divided by that factor, but since impedance of capacitor is reciprocal to the impedance of resistance, or is reciprocal to the capacitance, so this factor gets multiplied. Okay. Then we have the current source GMVB dash E. Then you have to resolve this resistance on the output side. I am showing it up here. It will be R mu divided by 1 minus 1 by AV. Then we have capacitor. If resistance is divided by certain factor, capacitance will be multiplied. Ct 1 minus 1 by AV. I showed you the reason, because reactance of capacitor is reciprocal to the capacitance. Then rest of the resistances R0 and RL. Okay. Now that means I have resolved the circuit into two parts. One is at the input and other is at the output. Now in order to find the cutoff frequency, what you have to do? To find cutoff frequency, you just have to find the resistance across the capacitance. So here if I ask you what is the capacitance at the input, it is diffusion plus transition into 1 minus AV. Both are in parallel. Okay. And what about the output capacitance? The output capacitance is simply Ct 1 minus 1 by AV. Okay. Now what you have to do is you have to find resistance across each capacitance in order to find the cutoff frequency. Okay. Are you getting my point? Like in low frequency response, what I told you, we have to find Thevenin resistance across each capacitance. For Thevenin resistance, you will short circuit the supply. So what is the input resistance if I see? It is RB parallel RB dash E parallel R mu over 1 minus AV. What about output resistance? Output resistance means resistance across this capacitance. It is R mu over 1 minus 1 by AV parallel R naught parallel RL. So these are the input and the output resistance. Is my point clear? Now you can find out two cutoff frequencies. One due to input capacitance C in R in. Other due to output capacitance 1 by 2 pi C out R out. Okay. Now the question comes, which frequency I have to take? Whether I have to take the input frequency or the output frequency. I told in the low frequency response that we consider maximum, but see here. The upper cutoff frequency represents a response something like this. Suppose this is FH1. Suppose this is FH2. So one frequency is saying it will pass all frequencies below FH1. Other is saying below FH2. So we have to take intersection. So which is the intersection? This region is the intersection. That means we have to take the frequency which is smaller of the two. So I'll say FH is minimum of FH1 and FH2. Is my point clear to you guys? So what you have to take is minimum in case of upper cutoff frequency and maximum in case of lower cutoff frequency. Now one thing that we have to understand here is, what is this AV? What is this AV in case of amplifier? AV is the voltage gain without connecting impedance between input and output. That means if you remove this impedance, that is if you remove this R and C, the voltage gain is AV. So you have to use the voltage gain derived without the use of impedance between input and output. So how you will do that? You will remove this impedance, then this will be a simple circuit. Find the voltage gain, and that voltage gain will be used in Miller's theorem. Okay, so is my point clear? We have to use the gain in the Miller's theorem, which is derived by removing the impedance connected between the two ports. So if we summarize what we have covered in this lecture, we have seen that at high frequency, which capacitances we have to consider? CD and CT, and other parasitic capacitance, or you can say other stray capacitances like wire and the lead capacitance. Then we saw the concept of Miller's theorem, in which I told the input impedance is Z over 1 minus AV and the output impedance was Z upon 1 minus 1 by AV. Then we saw dual of Miller's theorem, but that is not important from gate point of view or any other exam. Then we saw common emitter short circuit gain. It was coming out to be minus GM RB dash E over 1 plus SC RB dash E. This C was sum of the two capacitances CD and CT. Then we saw unity gain frequency, which was GM by RB dash E. This RB dash E is nothing but R pi. Okay. And we saw that when load is connected, resistive load is connected, we have to resolve R mu and CT at the input and output, and by use of Miller's theorem, and then we can find the two cutoff frequency, and overall cutoff frequency is minimum of the two cutoff frequency. Okay. But the most important part in this high frequency response is this one. Okay. So in the next video, we will solve some problems based on high frequency and the low frequency response, and you will come to understand that how to apply the concepts that we have learned in the frequency response. So this will be all from this video. Thank you. Hi guys, in the previous few videos I have told you about the frequency response of BJT amplifier, and in this particular lecture we'll work on the problems that are based on frequency response. Okay, so let us start with our first problem. An NPN transistor under forward active mode of operation. Why it is specifically saying forward active mode? Because there is another active mode which is inverse active mode. Is biased at IC equal to 1 milliampere and has ammeter base capacitance of 12 picofarad, base transit time 260 picosecond. We need to find the depletion capacitance of ammeter base junction. Okay. Now, when we talk about forward active mode, then what happens? The ammeter base junction is forward bias. Whenever any device is forward biased or a junction is forward biased, we define a diffusion capacitance for that junction. But due to depletion layer, there is another capacitance which it is calling as depletion capacitance. That is, if your depletion region is not completely vanished, there will be a depletion capacitance. That means the total capacitance is diffusion plus depletion. Is my point clear to you? If there is no depletion layer, then only diffusion capacitance. But if there is depletion layer, then there will be depletion plus diffusion. Now, this diffusion capacitance I taught you in the diode circuits. It was diode current into tau by eta Vt. Here this diode current will be the collector current 1 milliampere. Time constant tau, which is also called as lifetime, is 260 picosecond by eta taken as 1, Vt as 26 millivolt. So it will be 10 picofarad. Now the total capacitance is given as 12 picofarad. That is diffusion plus depletion, which means the depletion capacitance is 2 picofarad. So in such kind of problems based on frequency response, we have seen in high frequency response we are continuously using the diffusion and transition capacitance. Therefore, the expression that we studied in diode circuits of diffusion capacitance, that expression is very important in this section. The next one. An NPN transistor has beta cutoff frequency of 1 MHz, common emitter short circuit low current gain beta naught of 200, unity gain frequency Ft, alpha cutoff frequency F alpha. Okay. So see, what happens when we talk about BJT amplifier? Remember one thing, gain into bandwidth is constant. Now we have just studied the cutoff frequency and unity gain frequency. We were never talking about alpha cutoff frequency or beta cutoff frequency. What does it mean? It means when the gain is beta, the beta cutoff frequency is written as F beta. Since gain into bandwidth is constant, when gain is alpha, the cutoff frequency is F alpha. When gain is 1, the cutoff frequency is Ft. This should be same at all frequencies. So when you consider gain at any frequency, you have to take the corresponding bandwidth and the product will remain same. So now it has given us beta and the beta cutoff frequency 1 megahertz. So I'll say gain into bandwidth will be equal to beta into beta cutoff frequency 1 megahertz. So it is 200 megahertz. Now when we talk about unity gain frequency, the gain is 1. Unity gain frequency is Ft. So from here you can say that Ft is 200 megahertz. But then we talk about the alpha cutoff frequency. So we will write alpha into F alpha is 200 megahertz, where alpha is beta over 1 plus beta. Now here beta is 200, 1 plus beta will be 201. So you can say that alpha cutoff frequency will be 201 megahertz. Okay. So we have got unity gain frequency and the alpha cutoff frequency, and the concept behind such kind of questions that you always have to remember is the product of gain and bandwidth will always remain constant. Moving on to the next problem, it says the transistor in the circuit shown in the figure is so biased that the DC collector current is 1 milliampere. So it is not showing us the DC biasing network. It is saying that the DC biasing network is not shown. So that is why, since we cannot find the collector current by ourselves, it has given us the collector current as 1 milliampere. Then it has given us the network component values and BJT specification, beta equal to 100, base spreading resistance equal to 100, thermal voltage 25 millivolt. We need to find the voltage gain at a frequency of 10 kilohertz and input resistance for the two cases. That the capacitor across Re is 25 microfarad and when the capacitor is removed. Okay. Now we know the frequency as well as the capacitor. So let me try first case. In this, if you calculate Xc reactance is 1 by omega c. So 1 by 10 kilohertz means 10 to the power 4. 25 microfarad, 25 into 10 to the power minus 6. So it will come out to be 4 ohm. Now this Re is 100 ohm. So what happens? Re parallel Xce will be very small, because when we connect two components in parallel, their equivalent is less than the smaller value. So you can assume it to be 0, or you can say that Re gets bypassed. Is my point clear to you? We will assume that Re becomes bypassed because their parallel combination value is very low. Now, one thing that I'll do is I'll find the model parameters. Gm is ICQ by Vt. ICQ is given as 1 milliampere and thermal voltage as 25 millivolt. So 0.04 ampere per volt. Okay. Other than this, what parameter is required? If early voltage is not given, R0 is infinite. R pi is HFE by Gm. So HFE beta is given as 100. So that is 2.5 kilo. Now I will draw the circuit. If you see, this is the source with a source resistance 1.4 kilo ohm. Then this is the base terminal. Then I will show the base spreading resistor R BB dash. Then between B dash and ammeter, I'll show R pi, whose voltage is V pi. Then the ammeter terminal is grounded because it is bypassed. This voltage is GM V pi. R0 is infinity, so it will be open circuit. This terminal is collector. Then C, when you will ground VCC, this RC will be connected between collector and ground. And collector is connected to output voltage V0. Now what we want is the voltage gain V0 by Vs. So if you see, these three resistances are in series. So I can apply potential division. I can write V pi is Vs R pi over R pi plus RBB dash plus Rs. Now this R pi is 2.5 kilo ohm. RBB dash is given how much? RBB dash is given as 100 ohm and Rs 1.4 kilo ohm. 100 ohm means 0.1 and 1.4. So 2.5 by 4, 0.625 Vs. What about output voltage? Output voltage polarity is like this. But the current GMV pi, the GMV pi current is going like this. So the positive negative polarity will be opposite. You can say V0 is minus GMV pi RC. Okay. Now this V pi is 0.625 Vs. 0.625 Vs RC. So the voltage gain V0 by Vs is minus 0.625 GM RC. GM is given as how much? 0.04. What about RC? RC, if you see here, 2 kilo ohm. 2 kilo ohm I will write as 2000. So 625 into 2, 1250. 1250 into 4 is 2500. 5000 minus 50. Okay. So the answer to this will be, the gain will be minus 50. Is it fine? In the second part, what does it say? So let us go back and see the second part. It says that the bypass capacitor CE is removed, leaving RE unbypassed. So if we have removed the bypass capacitor, leaving RE unbypassed, so what I will do is, I will redraw the circuit considering RE. So I will start from the source resistance. This is 1.4 kilo ohm. Then there will be base spreading resistor, that is 0.1 kilo ohm. This is base, this will be B dash. Then we will have a resistance R pi. The voltage across R pi would be V pi. Now this is ammeter terminal. Now ammeter is not directly connected to ground, it is connected to RE. RE is 100 ohm. There will be a current source GM V pi. Then since R0 is infinity, it will be open. This is your collector terminal. The collector is connected to ground through a resistor which we call as RC, which is given as 2 kilo ohm. Okay. Now what we need to find here is, let us see. We need to find voltage gain and input resistance Ri. So I missed the input resistance part here. Ri. I told you Ri is always taken after the source resistance. If Ri is taken after the source resistance, it means it will be nothing but RBB dash plus R pi. That is 0.1 plus 2.5, or you can say 2.6 kilo ohm. Okay. Now, if we go into this part, what I can do is I can write this current as suppose small I, this current as capital I. This voltage is Vs. Now how can I find this small I? This small I is V pi by R pi, or you can say V pi by R pi is 2500. So that means 0.0004 V pi. This is small I. Now this capital I, by taking KCL, Gm V pi plus I, Gm is 0.04. So 0.0404 V pi. Now when you apply KVL, you will write Vs is 1400 I. I am going in ohms. Then 100 I plus V pi plus 100 capital I. So 1500 into 0.0004 V pi plus V pi plus 4.04 V pi. So it will come out to be 1500 into 0.0004 is 0.6 V pi, 1.6, so 5.64 V pi. Now when you talk about V0, you have to see that this current is going like this. Now polarity of V0 is plus minus, but due to current RC has opposite polarity. That means V0 is minus Gm V pi into RC. So that is minus 0.04 V pi into 2000 minus 80 V pi. So what is the voltage gain? V0 by Vs minus 80 by 5.64. So how much will this come out to be? 80 divided by 5.64. It will be 14.184. So it is much less than the earlier gain. Why? Because now RE is unbypassed and it is working as negative feedback, so it reduces the gain. What about input resistance? Input resistance will be taken from here. So here suppose the voltage is Vi. How you can find Vi? By applying KVL. That is 100 I plus V pi plus 100 capital I. 100 I is 0.04 V pi plus V pi plus 4.04 V pi. If you multiply capital I by 100, this equation, so it will be 4.04 V pi. So 5.08 V pi. And what about the small current I? I is 0.0004 V pi. So the input resistance is Vi by I, which is 5.08 divided by 0.0004. So it will come out to be 12.7 kilo. Okay. So that is how I can find out the input resistance. But remember, whenever you are taking Gm, Gm is in ampere per volt. So you have to take all the resistance in ohm. Don't take the resistance in kilo ohm. Okay, remember this thing. Whenever you are dealing with Gm, consider all the resistances in ohm and not in kilo ohm. Otherwise there will be calculation error. Moving on to next problem, it says an NPN transistor has unity gain frequency of FT 400 MHz, DC bias current 1 milliampere. We need to find its C mu. C mu is basically transition capacitance. Now what I told you is the unity gain frequency is given as Gm by R pi into, Gm by, it was Gm by C, not Gm by R pi, Gm by C. Okay, that was the actually omega t. In radian per second it was Gm by C, which means Ft would be Gm by 2 pi C, where C was CD plus CT. Okay. Now this CD is given as 0.3 picofarad. It is written as C pi. C pi means CD, 0.3 picofarad. We need to find GM. GM is calculated as ICQ by VT. ICQ is the DC bias current. VT is 26 millivolt. So 1 by 26. So FT is 400 megahertz. 1 by 26 into 2 pi into CD or CT plus 0.3 picofarad. From here, if you calculate the value of CT, it will come out to be almost 15 picofarad. Okay. So this expression for unity gain frequency is very important. You need to memorize this expression. Direct question can be asked based on this. Moving to the next problem. It says the figure shows a common base amplifier. Find the time constant associated with CB and CS and approximate lower cutoff frequency. Now, in order to find the time constant, we need to draw the AC equivalent circuit. In AC circuit, VCC will be grounded. Okay. But don't remove these capacitors. Okay, because when we are finding time constant, we need the capacitor. When VCC is grounded, this R1 and R2 both will be in parallel. So this will be R1 in parallel with R2. Then we have reached the base terminal. Between base and ammeter, what I'll do is I'll show R pi. This is base and this terminal is ammeter. Now ammeter is connected to another resistance RE and this terminal is connected to a capacitor, a resistance and a source. Okay, that is Vs. Now between ammeter and collector we will show a current source. Either you can show it as beta IB. If you show it as beta IB, I will show current here as IB. Ignore R0. Then there is a resistance between collector and ground. This resistance is RC and collector is connected to V0. Okay, and these two resistances are connected to ground. Now what it is asking us is to find the time constant of CB and CS. Now when you consider one capacitor, you have to short circuit the other. So I'll show you. For CB, we will short circuit the source Vs and the other capacitor Cs. So if you short circuit these two things, this will be like this. That means RE will be in parallel with RS. If RE is in parallel with RS, you can consider one resistance RE parallel RS. But this capacitor is connected to base, which means we have to refer this resistance to base. And whenever we refer the resistance to base, we multiply by beta or 1 plus beta. 1 plus beta is exact thing, beta is approximate. So what you can say is the resistance at the base terminal will be R pi is already there, and in order to refer this resistance, you will multiply it by 1 plus beta. So what I am actually doing is I am referring the resistance in the ammeter circuit to the base, and then this R1 parallel R2 will be parallel to this entire resistance. So you can say R Thevenin is R1 parallel R2 parallel RB. So what is tau base? It is RTH into CB. That is the time constant associated with CB. and it will have a lower cutoff frequency of 1 by 2 pi RTH into CB, suppose FL1. Now for another time constant and another capacitance. Okay. So I'll write down RB also here so that I can delete what I have already written. R pi plus 1 plus beta RE parallel RS. Now what we'll do is we'll now consider CS, but whenever finding Thevenin resistance we always short circuit the source. But since we are considering CS, we will short circuit CB. If you short circuit this capacitance, this resistance is removed. So what happens now? Now we have a resistance in the base circuit, that is R pi. Now I want to bring this resistance into ammeter. If you want to bring it to the ammeter, you have to divide it by beta, or you can say by 1 plus beta. Then it will be in parallel with RE. So you can say RTH will be RE parallel R pi dash, and then their equivalent will be in series with RS plus RS. So you can say tau S will be RTH dash into CS. And what about the lower cutoff frequency? The second lower cutoff frequency will be 1 by 2 pi RTH dash into CS. So we have found out the two lower cutoff frequencies and the two time constants, and then the overall lower cutoff frequency is nothing but maximum of FL1 and FL2. Lower cutoff frequency is always taken as maximum and the upper cutoff frequency is taken as minimum. Moving to the next problem, it says a NPN BJT has GM, C mu, C pi and DC current gain. Find unity gain frequency and F beta. Now unity gain frequency is simply GM by 2 pi C pi plus C mu. C pi is nothing but diffusion capacitance, and C mu is the transition capacitance. So it is 38 milliampere per volt by 2 pi. C pi is 4 into 10 to the power minus 13. C mu is 10 to the power minus 14. So how much will this come out to be? It will come out to be 1.47 into 10 to the power 10 Hertz, or you can say 14.7 gigahertz. Now it is asking F beta. There is no direct formula for F beta, but we know that gain into bandwidth is always constant. So beta is how much? 90 into bandwidth. I don't know the bandwidth, but it should be equal to unity gain into unity gain frequency 14.7 gigahertz. So it will come out to be, bandwidth will come out to be 0.1638 gigahertz. That will be your F beta. So unity gain frequency, you directly know the expression. For any other cutoff frequency, you have to make use of the gain bandwidth product. Keep that in mind. Moving to the last problem, it says consider the common emitter amplifier shown. The parameter of the amplifier are given. We need to find the resistance seen by the source Vs. Okay. So for that, I'll try and draw the equivalent circuit. C1 is given as infinity. C1 infinity means Xc, which is 1 by omega c, will be 0. So when I try to draw the equivalent circuit, first I start from Vs and Rs. Okay. Then since capacitor is shorted, I reach the base terminal. This is base. You will ground this 10 volt. When you ground this 10 volt, this RB gets connected between base and ground. This is RB. Now between base and ammeter we have a resistance R pi whose voltage is V pi. I am using hybrid pi model because GM is given. Now between collector and ammeter we have a current source GM V pi. Now ammeter is directly connected to ground. Then in parallel with GM V pi we have R naught, but R naught is given as infinite, so open circuit. Now see this RC. RC will be connected between collector and ground because now 10 volt is ground. So between collector and ground. Then collector is connected to capacitor C2. Then the load terminal is connected to a load resistance RL. Now it is asking us what is the resistance seen by the source. So if you want to find the resistance seen by the source, see from here, the resistance seen by the source is nothing but RS plus these two resistances are in parallel. So RB parallel R pi. What is RS? 1 kilo ohm. What is RB? 93 kilo ohm. What is R pi? R pi will have to be calculated as beta by GM. So 100 by 0.3861. So it will come out to be 0.259 kilo ohm. So 93K parallel 0.259. So 93K in parallel with 0.259 is approximately 0.259. So it will be 1.259 kilo. This resistance is very high. So parallel combination of a very high and a very low resistance is almost equal to the low resistance. Now it is asking lower cutoff frequency. So the answer here will be this. It is asking the lower cutoff frequency due to C2. For that we need to find equivalent resistance across C2. If you see, the resistance across C2 is series combination of RC and RL. So for RTH you will write RC plus RL. RC is 250, RL is 1 kilo ohm. So 1250 ohm. So what about lower cutoff frequency? 1 by 2 pi into 1250 into capacitance is 4.7 microfarad. 4.7 microfarad. So it will be coming out to be 27.1 hertz. The answer would be B. Okay. So remember, whenever you want to find out cutoff frequency, you have to find Thevenin resistance across the capacitor. And in high frequency response, we have seen we have to memorize the expression for unity gain frequency, and we have to remember that gain into bandwidth will always be constant. Okay. If you remember this much, you can solve any problem based on frequency response. Thank you.